just ticking over 50 viewers, and I think we'll make a start. So, if you can hear me okay, once again, just type something in the chat. I want today to be as interactive as possible, so type something in the chat, whether it's hello, an introduction about yourself, your favorite Mod 1 concept, anything, just type it in the chat, and we'll make a start. So, in case you haven't met me before, my name's Jeff. I've been posting a ton of content online for Catalyst. Basically, we teach HSC chemistry, prelim chemistry to students just like yourselves, and we do it pretty well. So we've helped about 250 students over the last 2 years, and we make learning chemistry super easy. The way that it basically works is we're a fully online program where we help you to learn content 3 to 5 weeks ahead of class pace, and that way you walk in the classroom knowing exactly what's going on by the time you're basically going to school. Our program is delivered, as I said, fully online. Our tutors are pretty good, and our results are also pretty good as well. As you can see on the screen, our results from last year, we had our top 6 marks all being 96 and above, going up to 98 for our highest chem mark in the end. We had a ton of high range 99 ATARs with our students in 2024. We're looking to do the same, obviously, this year with our 2025 cohort, but we haven't gotten those results because they haven't sat the HSC. We have a quick overview of why we do it so well. We have outstanding tutors. Everyone has a 96 or above HSC Chem mark. Our resources are pretty good, bulletproof in fact. You get access to our notes, our mock exams, all of our question banks sorted by dot points. You get to learn ahead of your class, which makes it much easier for your confidence and much easier to do well. And our classes are kept to small single-digit numbers and it's fully online, so you have very limited travel time and you get outside of class support through our community platforms. So that's a quick overview about what we do. I won't spend too much time here just because I know the main thing is the Mod 1 rapid review. But in case you are interested in signing up for next term, we run a Module 5 program and a Module 7 program in Term 4, and that starts on September 22nd. So today is September 6th. You've obviously all got your prelims, but if you're thinking ahead for next term and you want that head start to really get off the ground running for your Year 12 first assessment, that'll be the time to sign up for what we're doing. You can basically have a look through our website, send us a message on Instagram or by email if you want to ask any questions, and we'd be more than happy to help to guide you through the process. So that's pretty much what we do. The form to enroll is at the bottom of our website just here. Fill this out, we'll get in contact as soon as we can, and that's pretty much all I have to say. Any questions, type in the chat, but otherwise I'll get started with our Mod 1 rapid review. Okay, just pausing quickly to check the chat for any questions. Okay, cool. Let's get going. So, Module 1, Structure and Properties of Matter. It's a big content module, and if you don't have every little nook and cranny of this module covered, there's every chance in your prelim that you're going to get hit with a Mod 1 question that you just have no idea what to write, and you instantly lose all the marks. It's one of those modules where if you put in the effort and you learn everything, your progress hits like peak ability very quickly once you've gotten over the content hurdle, and the last, I guess, refinement is all just about working on how you write out what you know from your content. So this session will serve to cover all of the different areas that you might have missed in your revision, and basically what I would advise you to do is, as we go through today, when there are things that you realize, hang on, I don't know that, or I don't know that as well as I should, make a note of it, write it down, come back to it in your own study, and strengthen those weakness areas. So, to get into the module, the assumed knowledge before you go into prelim chem is that you should be able to talk about the states of matter, what a solid, liquid, or gas is, that a solid is, and how they behave as well. That solids are basically atoms that vibrate side to side in a fixed structure. Liquids then gain enough energy to break apart the lattice and move freely amongst themselves, but they don't have enough energy to escape and turn into eventually gas. When you have enough energy is when the atoms are able to then freely move from each other and they have no association anymore, moving as a gas. So it's all about the energy that matter basically has that dictates whether it can be a solid, liquid, or gas, and that's why we have melting and boiling points along the way. You should be able to talk about valencies and the crisscross method with how you basically find out the formula of an ionic compound. You should know your polyatomic ions. I think year after year, I'm always shocked at how poorly this is taught across the state. This is high leverage learning. If you haven't memorized your polyatomic ions, what you need to know is your ion name, the formula, and the charge of that particular polyatomic ion. Again, if you don't know any of these, it's a spot, like, you instantly will lose the marks. So you have to memorize all of these. I'd say the only ones probably a little bit lower yield is cyanide and then the ites. But the trick to learning the ites is it's always just the 8, so nitrate, with one less oxygen. That's how I remember nitrite or sulfite. It's the 8 with one less oxygen. Final thing is diatomic molecules. You have your 7. So genene is how I like to remember them. Anything ending with gen or ene, or you can use your acronym of have no fear of ice cold beer. Either's fine. These are elements that appear and exist as molecules where you have 2 atoms rather than just a single atom. And I would hope by now, at this stage of the year, we're okay balancing chemical equations. As a general rule of thumb, make sure that both sides have the same number of elements. And if you have elements that exist more than once on a side of an equation, for example, in this equation up the top here, you can see that you have oxygen existing twice in that equation. The trick to balancing any equation like that is to make sure that this element, the oxygen, you leave it to the end. You balance everything else first, and then the oxygen will balance itself. Trust me on that. That's how you would navigate those situations. The only case where you're going to have hard balances, where you have an element appearing more than once on a side. And I guess you could say it also appears twice on the left-hand side, which makes it even more of a point that you should leave that to the end. Okay. So into the start of the module, properties of matter. IUPAC nomenclature, I won't spend too long here. Ionic compounds, you name them as the cation and the anion. Typically the anion will gain the suffix of "ide" since it has now become an anion. And if you ever have polyatomic ions, you just name them as they are. So ammonium nitrate, for example, or ammonium chloride. Covalent compounds, you name them as the 2 nonmetals that you have. And you have to specify how many of that atom you have. Whether you have 1, 2, 3, 4, or 5 or more, they have a specific prefix which dictates what should be named. There's also a set of rules to decide what comes first, which are on the screen here. But what's more important is typically the prefixes. The one exception is the first nonmetal. So for example, if you had carbon and oxygen in carbon monoxide, you don't name it as monocarbon monoxide. The first nonmetal, if it only has one existing, you don't include the mono. So it's just carbon monoxide. But otherwise, if you had, for example, N2O4, that would be dinitrogen tetroxide. So just use the prefixes shown on the right to name the number of non-metal atoms there are. And that's pretty much all you need for naming. You can have a go at some of these if you want some practice. Won't go through all of them. All right. Mixtures and separation techniques. So we have mixtures versus pure substances. We should know that a mixture contains 2 or more substances, materials that are not chemically bonded together. Not chemically bonded. They just exist together. A pure substance, on the other hand, is just one type of molecule or atom, and it is the only thing that exists, hence it's pure. When we're talking about separation techniques, we're always talking about separations of mixtures. So we need to know the different types of mixtures you can have, and we also need to know the difference between homogeneous and heterogeneous mixtures, and that would allow us to decide what separation technique is best. A homogeneous mixture versus a heterogeneous mixture, the way that asks this in your exam is to maybe give an example of one, or talk about, basically define what the difference is, and you can take these definitions from our notes. A mixture that is homogeneous is one where the two substances, or more than two substances, are evenly distributed. Evenly distributed. So that could be tap water, where you have ions floating all around equally. It could be your cup of cordial, where you have the cordial molecules or ions or whatever's in there floating around equally in your cordial. That would be a homogeneous mixture. A heterogeneous mixture is anything where there is uneven distribution, so not evenly distributed. That could be your blood. It could be a bowl of cereal and milk. I think that makes it a really clear depiction, because if you have a bowl and you have your cornflakes sort of all floating around and lumped up in the middle, and then you pour your milk in and the milk just sort of sits in down the bottom, that is not evenly distributed. You've got milk mixed with cereal at the bottom, there's cereal pile on top. It's completely uneven, and that's how I like to visualize a heterogeneous mixture. Okay, as I've said before, any questions, any comments, just type them in the chat as I go along. I can see the comments as they come up, so leave them as we go. There are then two types of pure substances that we should also define: element versus compound. I think there's a lot of misconception around this early on in prelim. So in terms of what an element is, you should know that it is a pure substance that is only one type of atom. One type of atom only. That could be an iron. A sample of iron is just an element. When it changes to a compound, that is where you have two or more different elements combined in a known fixed ratio. So that might be an ionic compound. It could be a covalent compound. There are two types of compounds we talk about. We'll talk about this a bit more later, but just as a quick overview, compounds can be either ionic, they can be covalent, and as we talk about later, we have covalent molecules and we have covalent networks. These are all different configurations of compounds. And I think the number one misconception is that a molecule is the same as a compound. This is not the case. A molecule, as we later talk about, are individual entities that repeat OH, such as water. They are individual, separate entities. They are not lattices. And that is why a molecule is different to a covalent network, because a network is a continuous lattice-like network. An ionic compound forms a continuous lattice-like network, but a molecule is individual entities of grouped atoms. Okay. Cool. So we've talked about our types of mixtures, we've talked about our pure substance types. Let's get into the separation techniques themselves. Separation techniques separate by physical properties. So physical properties are any property that can be observed without a change of the identity of the substance, or without no change in chemical composition. Composition. That could be your melting point, boiling point, density, solubility, magnetism, all important physical properties which we separate using. So based on what type of mixture you have, whether it's a mixture of solids, liquids, or a mixture of both, it could be dissolved substances, you're going to pick your separation technique based on what properties the different substances have. So in the case of solids, you have three options. Sieving. Sieving separates by particle size. So big particles get caught in the sieve, smaller particles pass through. Magnetic separation separates by magnetism. Iron is going to be drawn to a magnet while sand is not, so that would work. And the last one is separation by solubility. So if one substance is soluble, the other is not, you're going to use dissolution potentially. If, for example, you had NaCl, salt, in solution, and you added water, that would dissolve the NaCl into the water, separating it from the sand that's at the bottom. So, three different properties. Understand that any separation technique, when you write about it in your prelim exam, you have to be able to justify it in terms of the property you're separating by, as well as the states of the matter that you're separating as well. Okay. Separating solids from solvent. Evaporation or crystallization are the two things you can call this. Basically, you're boiling off the liquid, leaving behind a solid. Separating mixtures of solids and liquids. You have a few options here. Decanting, basically just tipping out the liquid until you get left with the solid at the bottom. Filtration, which is pouring through the liquid with the solid at the bottom, so the suspension getting poured through filter paper. And the filter paper would catch the solid within it, whilst all the liquid passes through to the bottom. A key part of filtration that often gets left out is that once you've left this solid in the filter paper, what's a potential source of error if you just leave that solid in the filter paper and use that as your final sample? Say you want to go and weigh it. Why would that be problematic, and how do we fix it? Type in chat. How can we fix that? Oh, is the audio really quiet? Can everyone let me know if the audio is quiet? Or is it... a little quiet? Okay, let me see if I can bump it up. Okay, hang on. Is that any better? I'll keep bumping it up if it's not. Not really. Okay, let's try again. Okay, is this any better? I think I can see the volume going up. but it's still, I can see, is a bit quiet. Let me push it even more. 20. Is this any better? Okay, great. Thank goodness. And yes, everyone who's commented in the chat that weighing the filter paper beforehand and weighing the filter paper would be the first thing you need to do, weigh it beforehand. The second thing is that the filtrate is going to be wet. It's going to have liquid in it. The water is still going to be all in that filtrate, which means that in order to get an accurate mass, you have to dry it out. So whether that would be placing it in an oven, letting it dry on its own on a windowsill, an oven is probably best, given that it will be a bit faster and more complete. That would help you to get a accurate sample in the end. Okay, and thank you everyone for letting me know that it was a bit quiet, and glad to hear that it's better now. The final technique is centrifuging. So centrifuging is where you basically use centripetal force in order to separate out solids to the bottom of a sample. This is how we separate the different components of blood product, where you have solid red blood cells that can collect at the bottom and plasma on top. But basically it separates solids from liquids using their densities as well. And the final separation technique is separation of liquids. You have distillation and you have a separating funnel. Distillation separates by using boiling points, where if you have a liquid with a boiling point, say two liquids within a mixture, one with a boiling point of 100 degrees Celsius and one with a boiling point of 150 degrees Celsius. If you use a heat source and you heat it up to 120 degrees Celsius, the substance with a 100 degrees Celsius boiling point will evaporate, and it can be collected in a separate sample through a condenser which turns it back to liquid, ultimately separating out that substance on its own. The substance with a high boiling point, 150, will not be boiled since we're still below its boiling point. We might have a little bit that does boil off, given that temperature is an average of kinetic energy, but for the most part, most of it will not evaporate. The second technique through a separation funnel is where you separate mixtures that are, number one, insoluble. So they have to be insoluble mixtures with each other. And if you know what makes two liquids insoluble with each other, type it in the chat. And they have to have different densities. The substance with a higher density will sit on the bottom. The substance with a lower density will sit on top. And when you open up the stopcock and you allow the liquid on the bottom to start flowing through, eventually all of this will have passed through. You would close the stopcock, and that leaves just the high density liquid inside the separating funnel, and you can collect a separate sample of the high density liquid in a separate container. So Suresh, nag, sag, and snap. Nag, sag, more so that's for ions and dissolution in, so ionic dissolution is nag-sag, I would agree. But when we're talking about two liquids dissolving in each other, it's a little bit more complicated. And it's to do with the rule of like dissolves like. Yes, Kev, perfect. So Kev's on it. Polar molecules and non-polar molecules is what will decide whether you have two liquids that are soluble or not with each other. If you have a polar solvent, or you have two polar liquids, and we'll talk about how you determine if a molecule is polar later on today, because that's really important. If you have two polar liquids, they will dissolve in each other. Like dissolves like. If you have two non-polar liquids, they will dissolve in each other. They dissolve as well. But if you have a polar liquid and a non-polar liquid, they will not dissolve in each other. So a polar does not dissolve in a non-polar liquid. We'll talk about that more later on today. Okay, so that's all of our separation techniques. Fractional distillation, not overly important for our context in prelim. This is more of a year 12 extension concept, but we arrive at mass calculation. So mass calculations, you have your percentage component calculations, where you get given a total mass of sample, so you have 100 grams of it, and you get told that a certain component takes up 16.00 grams in that total mass. To find the percentage component, you simply place the mass over the total mass to give you about 16% once you multiply by 100%. You can also take this concept of percentage composition and use it to find masses given a total mass. So if you got told that you have a 152 gram sample and it's 37% iron, you would be able to find out that the mass of iron, and if you're not already using shorthand for your calculations, start using it. Saves so much time. So what this means, for those who haven't seen it before, little m means mass, and if you put brackets behind it and anything within the brackets, it means mass of iron. That's really what this reads as once you use the shorthand. The mass of iron can be found to be 152 grams times by its percentage, or you can do it as 0.37, and that will give you your answer out at the bottom. Okay, here's a question if you want one to try on your own. Here's another one. Here's another two. Save these for later if you want. And the work solutions are all down here. Okay. You should know how to perform a gravimetric analysis. As I said before, when you're doing a filtration, the steps that you need to go through are pouring the suspension through the filter paper, capturing the solid in the filter paper, making sure that you weigh the filter paper beforehand in order to subtract its mass, dry out the solid because it will still contain water, and then using the mass, we can then move on, we can find what mass of solid you have left, and that's important once we start to talk about our mole calculations in a little bit. Okay. Chemical and physical properties. As I said before, a physical property involves characteristics of a substance that don't have any change in the identity, the composition of the substance. So there's no chemical change. What I mean by that is if you were to take an ice cube, you take an ice cube and you melt it down to liquid water, you are not changing the chemical formula of H2O. H2O solid is just being turned into H2O liquid. You are simply changing the way that that molecule behaves. There is no change in the composition in the same way as if you were to do a reaction and take hydrogen gas, react it with oxygen gas and form water, balancing. This is a chemical reaction and a chemical property of hydrogen and oxygens that they're able to react with each other in this way. It's a chemical property because you end up with a product that has a different chemical composition. So all of these chemical properties down below involve some sort of change in composition, and that's what makes them chemical. Yes, they are hard to reverse, but that's not what defines a chemical property, because some chemical reactions can be reversed, as we find out next year in Module 5. Okay. At this point, the syllabus introduces the periodic table. The periodic table splits all of the elements we know about into three big categories: metals, metalloids, and nonmetals. And each of those categories tends to have a set of properties that they more or less follow. This table captures it, and the graphic just up above here shows how it splits. You can sort of see there's a metalloid line running, and they're also referred to as semi-metals, these metalloids. They run down the diagonal there, and you have your metals, non-metals, either side of that. importantly noting that hydrogen is not a metal, it is a non-metal. The properties of these, which you should know, I would say, these are important for your prelim. You should know the properties of metals and non-metals in terms of their appearance, their electrical conductivity, thermal conductivity, malleability and ductility, density, boiling point, strength. Generally speaking, these are all properties you should know. Don't worry about semi-metals, I would say. Schools will tend to not ask these because there's such variability between them. It's not really worth asking. But metals and non-metals, you should know these. We'll explain these in more depth later. You should also know the periodic table families, as well as what we refer to as groups and periods. A group refers to a column, so group 1, 2, 3, 4, 5, 6, 7, going all the way through to 18. These are all of your groups. Sometimes you also see the groups on the right simplify down to 3, 4, 5, 6, 7, and 8, instead of 13, 14, 15, 16, 17, 18, just excluding the transition metals. So be aware of either of those configurations. Then you have your periods. A period is your horizontal row. Each of these going across is a period, again, numbered 1 through to 7. Okay. You then have names for groups of these, for the different regions of this periodic table. Group 1, alkali metals. Group 2, alkaline earth metals. Transition metals, group 3 to 12. These will typically all behave relatively similar. Transition metals, there's a lot more difference between the properties, but for the alkali and alkaline earth metals, the properties are pretty much all the same. So you should know these properties as listed on the screen well. You should know that their physical properties are as shown. The important ones, I'd say, if I was to go through, that you must know, are that alkali metals have high thermal and electrical conductivity, relatively low melting point, and in terms of the chemical properties, they are highly reactive, highly reactive, and it gets more and more reactive as you go down. Cesium is the way I like to remember it. Cesium, if you've ever seen it dropped into water, it's basically a massive explosion. And if you go back up to the higher ones, sodium, lithium, if you drop them into water, they sort of fizz around on the surface and sort of spit. But cesium, if you drop it in, it has to be cased in a really protective casing, otherwise it will just explode on its own. But when you do put in water, it's very highly explosive. Alkaline earth metals as well, I would say that the important properties here as well would be the high thermal and electrical conductivity, that they have high melting points and they're harder than alkali metals, and similarly they're also reactive but not as reactive. Those are essential. The other ones are helpful as well. And finally, transition metals, they're quite heterogeneous, but similarly high thermal electrical conductivity, high melting points, and we can explain that later. If you know the reason why for this, type it in the chat, test yourself. Why are metals conductive of both heat and electricity, and why are their melting points so high? Type it in chat. I wouldn't give too much thought, as I've already mentioned, to the post-transition metals as well as the semi-metals or metalloids. These don't really get asked, but what does get asked all the way on the right is the halogens and the noble gases. So halogens, group 17, they have 7 valence electrons. Their physical properties tend to be that their boiling points and melting points are going to be lower. They're going to actually increase as you go down, and we should know their states, as I'll show a little bit later on. They are reactive, but in a different way to metals. Metals react when they lose their electrons, whereas halogens and non-metals on the right will react when they gain electrons. So that is an important concept which we talk more about in Module 3, which you should have also seen by now. Noble gases, finally, all the way on the right, inert. They're called inert gases because they're not reactive. Low boiling points, low densities, and typically they're monatomic, so they only exist as one atom on its own. And yes, so those of you who said delocalized electrons, brilliant. So yes, Will, Suresh, Tilly, Samantha, very good. Oh, Samantha for a different reason. The sea of delocalized electrons allows charge to move freely around the metal lattice, because that's what conductivity is. So if you have a metal lattice like this, and you have an electron bumbling around that's able to move, that gives you the property of conductivity for electricity. If you have free moving electrons or free moving ions in solution, conductivity is the ability to have free moving charge. And then with what Samantha said, the metallic bonding is what gives them their high melting point and their hardness. And I guess the only other property that's not mentioned here is the malleability. Malleability is because the sea of delocalized electrons acts as like glue. So if you were to hit and strike the metallic lattice, it will deform, and the sea of electrons sort of just holds it in a new position. It doesn't shear and shatter. Okay. Cool. Second inquiry question. Atomic structure and atomic mass. We have atoms, and we have isotopes. What else would I say if I were to answer 3 mark about conductivity? Pretty much what I just said, I think. I would talk about, as I said, the sea of delocalized electrons. I would talk about how conductivity refers to the ability for a substance to have free moving charge. And therefore, a metal is conductive because the delocalized electrons are free to move, which means that electricity can therefore be conducted. That it obviously depends on the exact question, but those things are the things that I would look for as I mark a response on electrical conductivity for metal. Okay, atoms and isotopes. Firstly, what is an isotope? Can everyone type this in chat before we reach it? What on earth is this? And then what even is an atom? An atom the definition of an atom has gone through significant change from its early models of Dalton's model all the way through to Schrodinger's, which is the last one we talk about in the syllabus, and physics focuses a bit more on, but for us, we sort of just mention it, and we talk about some evidence supporting it, but we talk more on Bohr, and Bohr's model is really the focus of what our chemistry level understanding of the atom needs to be in prelim. And yes, so good, everyone who's saying different number of neutrons, same number of protons, yes, that's what a isotope is. So, for the models, what I would recommend you know is a quick definition of each of the models. So, going through from start to finish, talking through each of these, Dalton's being that atoms were indivisible, solid spheres. Thomson then talked about how there's the electrons in his plum pudding model. Rutherford talked about how there was mostly empty space and a positively charged something in the middle, which he dubbed the nucleus. Bohr's model then expands on Rutherford's, and he says that instead of these orbiting electrons that go around the nucleus, that's impossible, disproves it, and he says instead that these energy levels or shells that exist around the nucleus. And finally, Schrödinger then goes on to say that, hang on, all we know is that electrons exist in regions of space, probabilities, and in fact they have wave properties, but that's venturing into physics, we won't go there. That's pretty much a quick summary over all of these atomic models. If you don't know any of them, go back and have a quick review. So to summarize, our understanding that we take into prelim chem is that an atom consists of a small dense nucleus in the middle, and there's a cloud, there's clouds of regions that could possess electrons, and we call those clouds orbitals. These electrons exist in energy levels, so they can be excited to higher energy levels, but they will try to exist in the lowest energy levels possible, and that's pretty much our understanding. And then there's a nucleus in the middle, of course, that has the positively charged protons and neutrons, as well as all these electrons that exist in the orbitals around the nucleus. Atomic symbols. We have to be able to interpret these. There's 2 numbers and a elemental symbol. So what they mean, the bottom number is your proton number, your top number is your proton plus neutron number, and your letter is just your element that is defined by the number of protons you have. Type in chat quickly, how do you find the neutron number, therefore? And we'll move along. We have isotopes. Isotopes are atoms, as we've said, with the same number of protons, different number of neutrons. So, that means that you can have different versions of, for example, hydrogen, where you have one proton in each hydrogen atom, but you can have either 0 neutrons, 1 neutron, or 2 neutrons in each of these, and as everyone's saying, it's mass minus atomic number to find the number of protons. Mass minus proton number, good. And that would give you the number of neutrons. So these are all isotopes. You can get isotopes either naturally occurring, or you can get them from artificial sources, such as neutron bombardment is one way, where you can basically add on neutrons. But for our purposes, we just need to know that isotopes exist, and there are two that we can get them either naturally or artificially. Given that we have isotopes, this then allows us to explain something called relative atomic mass. Before I go and explain it, if you know the answer, type it in the chat. Relative atomic mass refers to that number you see on the periodic table. So for carbon, the atomic mass, or relative atomic mass, you note is 12.01. It's not 12.00 or a fully rounded number. And the reason for that is because relative atomic mass takes into account the average atomic mass of all carbon in existence. The average atomic mass of all carbon in existence, and yes, it is relative to a carbon-12 isotope. So that when we look at all the isotopes of carbon, it makes more sense. We have about 99% that exists as carbon-12, which would have a mass of 12.00. We have about 1% that exists as carbon-13, which has a mass of 13.00, given 13 protons and neutrons. And then relatively negligible amount exists as carbon-14. So the average relative atomic mass, well, the average atomic mass of all of this carbon taken into account, ends up being, to calculate it, 12.00 times 0.99 plus 13.00 times 0.01. And that will give you 12.01 as we expect. Atomic mass units is the relative atomic mass. So understand what relative atomic mass is, understand how to calculate it, and that will leave you in good stead for these questions that come up inevitably. So some practice questions. Here you go. Practice question, practice question. You can have a go at those in your own time. Properties of isotopes. We then understand that isotopes can be radioactive and they can be stable. It entirely depends upon the ratio of protons and neutrons. It entirely depends on the ratio of protons and neutrons to decide whether an isotope is stable or not. What you need to know about isotopes is you need to know the types of radiation you can get. Type those out in the chat as well. What are the types of radiation you can get? The three main ones, is also one extra one that sometimes comes up. And then you should be able to therefore balance a nuclear equation. So first of all, a stable isotope, because that's easier to start from. A stable isotope is an isotope where the forces holding together the atom are balanced and the atom is at its lowest energy state. So the carbon exists in, for example, carbon, can exist in carbon-12 and 13 as stable isotopes, and the ratio of protons to neutrons has to be 1 to 1 or very, very close for any elements up to 20 protons. So that's why carbon-12 is stable, because it has 6 protons to 6 neutrons. The ratio gets closer and closer to 1.1 to 1.5 once we get closer to 82 as our proton number. And you can visualize this on a band of stability. I think I'll just jump to that because it's probably something you've seen before. Don't have to build up to it. Band of stability down here. And yes, everyone who said alpha, beta, gamma are correct, good. And no one said positron, but positron was the last sneaky one that they can also ask. You have the band of stability, which shows you, going down the middle, these black squares. These are your stable isotopes, where the ratio of protons and neutrons is stable. These will not decay. And every single isotope is trying to get to this band in the middle. Every other isotope that is not one of these black ones going down the middle is unstable, and they will undergo decay. That is the importance of the band of stability. It tells you what is stable, what is not. And you can see, based on the colors, what type of decay substances undergo. As a gross generalization, most commonly, this is the way things will decay. If it's to the right of the band of stability, it will undergo alpha decay because you have too many protons and you have too many neutrons. If you have an isotope above the band of stability, you will undergo beta decay, because you have too many neutrons to protons. And if you're underneath the band of stability, typically you undergo a positron emission, which is the E+, positron, or beta plus you might see as well. That will reduce your proton number, increase your neutron number, and bring you back towards stability. Okay, so then what are those types of decay? To quickly recap all of that, your types of radiation: alpha, beta, positron, and gamma. Each of them are different properties. Basically, we separate them by their penetrating power, which is how well they go through different substances of different thicknesses. Alpha is the least. Beta and positron are similar, and gamma penetrates more than the other two. We also need to know about the deflection by magnetic and electric fields if you wanted to go for that really high level mark. Some schools will ask about this. But essentially, if you have each of these particles being shot through an electric or magnetic field with velocity, they get bent by the magnetic field into a circular motion if they have charge. So beta or positron and alpha, these will all get bent. The positive particles get bent in the same direction because they have the same charge. Negative gets bent in the opposite direction. Whereas a gamma radiation will not get bent because it has no charge. Similarly, for a electric field, so if you have a system with two electric plates and you shoot radioactive particles through it, you will see that beta particles will get curved, but this is a linear acceleration, not centripetal motion. It's physics stuff, doesn't really matter too much if you're not doing it. And alpha gets bent the opposite way because it has the positive charge. Whereas once again, gamma has no charge, so it does not get bent by the electric plates. So a very nice summary table here. You need to know these things about each of the types of radiation. What type of matter they are, their symbol, the velocity, whether they travel at the speed of light or not, basically. That's what C means. C is the speed of light, and these travel close to the speed of light, whereas alpha is much slower. You need to know their penetration. You need to know what's able to block it. You need to know their charge. You need to know how they're deflected by an electric or magnetic field. And then, once you know what the particles are, you can then talk about how the decay works. You can write the equations based on this general idea that a parent nucleus will decay into a form of radiation plus a daughter nucleus. Daughter nucleus being the isotope, or it may not necessarily be an isotope, the yeah, a different isotope, I'll put it that way, different isotope that is typically slightly more stable compared to the parent. Question in the chat from Isabella. If something just refers to beta radiation, is that positive or negative? It will typically refer to negative if they don't say positron specifically. If they say beta radiation, I would read it as negative. Okay, so the types of decay. Alpha decay. Alpha decay reduces both your proton and neutron number, which means that you go from, for example, radium-226 goes to an alpha particle, which is your radiation, and the daughter nucleus, which is just the parent, take away the two numbers. So 226 minus 4 gives you 222. 88 minus 2 gives you 86. And that's how you find your atomic and mass numbers for the daughter nucleus, which allows you to then identify it's going to be radon if you are asked to write that equation out. Do you have to write the H, E, and E, or can you just do alpha and beta? You can do either. Either is fine, as long as you keep it consistent with your whole paper. So if you do beta in one place, do beta through the whole paper. If you do alpha in one place, do the same thing through the whole paper. And at the end of the day, your teacher is the one marking your exam internally, so ask them what they prefer if you're ever unsure. Beta decay, when your neutron to proton ratio is too high, decreases the ratio. So similar rule of thumb with the daughter nucleus. Positron gives you, as shown here, carbon 10, we've got a boron 10, for example, and gamma decay is just where you have too much energy. A gamma particle or gamma radiation gets released just to bring back down energy, and typically that will actually leave you with pretty much the same thing, just without the excited state. An excited state can be notated by an M, it can be notated by a asterisk, and gamma just releases some of that excited energy. Okay, cool. So pausing quickly, any questions in the chat? Let's have a sip of water. And how are we all going? Is everyone going okay with the speed? Anyone go faster, slower? Or are we happy at the moment? Okay. Cool. Speed is good. We'll keep it going. So, discrete energy levels, electron configuration, SPDF. This is pretty important to understanding how electrons configure themselves around the nucleus. We understand through Bohr's model that we have these discrete energy levels, and we have to be able to talk about that. So, at the center, we have our nucleus for any atom, and it's surrounded by all of these shells or energy levels which contain a number of electrons within them. Going 2, 8, 18, 32, your trick to remember them is that it's 2n squared, where n is the number of the energy level. So that is a trick you can use to remember. So you should first be able to write out principal energy level electron configurations, where you go and talk, for example, sodium having 2 in its first energy level, 8 in its next, and 1 in its third. And you're filling from lowest energy level up to highest, going to the next energy level until they fill up. The valence shell is the outermost shell of an atom. That wasn't entirely clear. And then we start to get in some important terminology. Subshell. So every energy level is split into subshells, which are split then into orbitals, or contain orbitals rather. So subshells are your S, P, D, F, and so on. Each of these subshells has a particular number of orbitals. So an S subshell contains one S orbital, a P subshell contains 3 P orbitals, D, 5, F, 7. And within each of these orbitals, you have a fixed number of electrons. Every orbital holds 2 electrons. Every orbital holds 2 electrons. And so if you have one orbital in a subshell, that means a subshell holds 2 electrons total, since there's only 2 electrons in that one orbital. If you have 3 orbitals, you can hold 2 in each, which means the subshell P can hold 6 electrons. And the rule is that each energy level holds one more subshell than the next. Subshell 1, or in energy level, there's only a 1s. In energy level 2, there are 2 subshells, a 2s and 2p, which is why you have 8 electrons in the second energy level, and so on. 3s, 3p, 3d in the third, which is how you get to 18, and so on. For how you think about an orbital, we've said that there's 2 electrons in each, but we also need to be able to visualize that. An orbital is a region of space that the 2 electrons within it are most likely to be in. They're not 100% certain going to be there. There's every chance that the electron could be outside of that orbital region. It's just the probability of it being in there is the highest. And each of those subshells has a specific shape, or specific orbitals have a specific shape. You don't really have to know these, just understand that this is the way it is. Okay, so we now know that there's shell that holds a various number of subshells depending on which shell it is, and each of those subshells holds a specific number of orbitals that each hold 2 electrons. Okay, a few questions in the chat. How long is this review? Until 10:30, that's the scheduled time. We'll probably go a little bit over, probably 10:45, before we go on to Mod 2 at 11. We will spend time on inter and intramolecular forces for sure. How do you know whether 4s or 3d will be filled first? Great question. We're about to get onto that. So 4s would be first because it is slightly lower in energy compared to 3d. And that comes through this diagram here. This is really visual. I like anything visual is great. So that's why you fill 1s, then 2s, then 2p, then 3s, then 3p. But hang on, it's easier to fill up 4s than it is to fill up 3d. That's the way it will go. Can we use the arrow diagram? Yes, we can draw some spin diagrams in a second. Pauli exclusion and Aufbau principle, yes, those are important. And yes, we'll get onto intro and inter. We'll spend more time there at the end. So, SPDF, the ordering as is shown, you can draw spin diagrams following 2 rules, the Aufbau principle and Hund's rule. Aufbau principle says that electrons fill in a way to minimize total energy. So that's why we go from lowest energy up to highest. And Hund's rule says that the lowest energy configuration involving orbitals of equal energies is the one with the maximum number of unpaired electrons with the same spin orientation. So that is why we would, for example, fill up for 2p all of the upspin electrons first in order to pair them all up in the same spin orientation instead of going one and then pairing. That is less favorable than it is to go upspin, 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 and then start filling in the downspins. it is more favorable to fill in the up spin all first. Okay. 4s is not always before 3d. There are 2 exceptions. And if you know the 2 exceptions to that, type them in the chat. So it's a good question, Lucy. And then we get onto SPDF notation, as we've said. When you write this out in your exam, you'll be writing out a configuration of each of these where you have the energy levels with the subshell specified and the number of electrons inside is the number at the top. You then have each of them going on until you run out of electrons. In this case, we've run out at 3d2. Yes, copper and chromium are correct. Copper and chromium are your 2 exceptions. So copper and chromium are the only case where you will fill 3d either half or fully full before you fill 4s full. Okay. Upspin and downspin, just understand there's 2 ways you can configure an electron inside an orbital, either spin up or spin down. And beyond that for prelim level, it's probably not worth at this stage going into it too much, but for the way we draw our spin diagrams, your understanding is just that you fill in an upspin electron, you fill in all the upspin electrons first, which is pointing upwards with an arrow, before you fill in any that are pointing down. That's what we need to know. I wouldn't worry too much otherwise from that. And as we said, the 2 exceptions are copper and chromium. You should know that copper and chromium are it's more favorable to fill the 3D shell half full or either full before filling 4s. So you end up with a 4s1 instead of a 4s2, 3d9 or 3d4. You end up with 3d5, 4s1, 3d10, 4s1 instead. Okay, cool. Quick summary. And we get on to Bohr and Schrodinger's models. What you need to understand with these models is, as we said, what they are, but also how you show that they are correct using spectral evidence. So for Bohr's model, Bohr said that there are 4 main things. He said that electrons exist in fixed orbits around the nucleus. They are not actually spinning around and round. Each orbit has an energy level, so that's discrete. Energy is absorbed and emitted when an electron jumps or falls back down between energy levels. And you cannot have electrons that exist between energy levels and orbits, only within the actual energy levels. The spectral evidence for this model is emission spectra from hydrogen, which showed that there were different colored light waves that came out when you excited hydrogen. And for any sample of hydrogen, it was always the same wavelengths of light. So what was happening is that electrons were being excited to higher energy levels, and when they fell back down, they would emit a fixed amount of energy, which would give a specific wavelength of light every single time. So you get a violet light, a green light, a red light as part of this Balmer series, which is what it's referred to as. And that was one of the most important discoveries for supporting this model. Do we need to know how to interpret emission spectra diagrams? I would say it's not out of scope. You just need to understand that that's each of these wavelengths of light come about because of a falling of an electron from an excited state to a less excited state, which gives you a discrete wavelength of light, discrete packet of energy, which reflects, or it gives you a specific color for any specific element you will have in emission spectra. Okay. Bohr's model was not without limitations, as a few listed here. And then Schrodinger's model comes in and says that basically you have, as we said, these orbitals, these probability regions where electrons should exist. And he talks about the wave-particle duality as well. Again, sort of going beyond the scope. If your teacher's talked about it, learn it, but otherwise, I usually don't even worry about it. Okay. Quick interjection with the way you're studying. In this last week, you should be focusing on entirely questions. Once you've finished a little quick review of your content with us, it should be all questions. All questions. So do past questions. Use our question compendiums if you have them. And that is the way that you're going to improve in these last few weeks. But not just doing questions, you have to mark them, you have to correct them, and you should also be tracking your questions that you get wrong in some sort of form, one way or another. If you set up this habit early now, by the time you get to your trial next year when you've banked up a list of, say, 100, 200 pages of questions, which is what I ended up doing, and I only started halfway through year 12, which I really regret. Once you've banked up those questions and you have all these mistakes and questions that you've once found difficult, every time you revise and you come back to look at questions that you once got wrong and you look at the corrections, how you would get that right the next time you saw it. This is number one, only addressing weaknesses. That is what you want to do with your study. Be efficient. Only address your weaknesses. And number two, it is cutting out silly mistakes. Because a silly mistake is not a silly mistake. It's just you haven't properly corrected in your head internally a mistake you've made before. So that would be my advice for your study in this last period. Focus on questions, focus on corrections, and that would be how I'd go about it. Okay. Just checking any other questions. Don't think so. Okay, periodicity. Know your periodic trends. You should have seen some sort of diagram that resembles this one, talking about your electronegativity, talking about your ionization energy, talking about atomic radius and reactivity with water to some extent. So, you should be able to talk about which way these trends will occur as you go along left to right, top to bottom. You should also be able to explain it in terms of shielding and nuclear attraction. This is where the students who are getting 90 plus separate themselves from those who are getting 70 or 80. They're just able to explain things better because they know what's actually happening. Just quickly before we get into that, you should know the states of matter of different elements at room temperature. As shown here, the only liquids are bromine and mercury. All group 8 elements are gases, and all of the other elemental gases are nitrogen, oxygen, fluorine, chlorine, and hydrogen. Everything else is then a solid, and that's your states of matter at room temperature. It's obviously a little bit harder for compounds, but for elements you should know what the state of something is. If, for example, I said, what's the state of aluminium? You should know that that's a solid. Or if I said, what's the state of neon? You should know that that's going to be a gas. Electron configuration. We've already talked about how it's configured around a nucleus in the middle, shells, energy levels with subshells, orbitals, and the electrons in the orbitals. So going from left to right, we should know that the way that it's working is if we had an element with a nucleus in the middle, and we have an inner shell of electrons, so we have 2, and an outer shell, let's say starting with 3 electrons. As we go from left to right, each electron is going to get placed into the outer shell, so into the valence shell as well, probably more correct to say. Each additional electron gets placed into the outer shell until we hit a full valence shell. At this point, we are now going to go from one period down to the next period all the way on the left. I think my camera is inverted, so if I'm doing it the opposite way, I don't mean to. You would then open up a new shell where you add in your next electron. And now you have a new valence shell, you've gone to a new period, and you're going now from top to bottom. So the idea is every time you go down one period, you are adding on an extra shell. And that's the way that electron configuration works. You go top to bottom or left to right. Then, we have to understand shielding. Can everyone type in chat a quick definition or one-liner about what you think shielding is? Test yourself, and you can always catch up to the live once we get to it. Shielding talks about how the electrons on the inside of an atom will repel electrons that are on the outside. So, because all these electrons are negatively charged, we know that negative charge will repel negative charge. The inner electrons push out electrons that are further out from the center, and that force is shielding. And that shielding is really important because it gives us the different properties of our elements, including ionization energy, atomic radius, and your reactivity as well. In combination with one other factor, which is your nuclear charge, this defines how strongly a valence electron is going to be held. So your effective nuclear charge, which is sometimes notated as ZF, is equal to, grossly speaking, the number of protons in the nucleus take away the number of core electrons inside of that valence shell. So, if you have lots of protons, this will have lots of attraction. So this is a measure of how strongly they're attracted into the center. S, shielding, refers to the repulsion from the center. So these two factors sort of butt heads with each other. They're fighting against each other to determine how strongly an electron is either held or repelled from the inner parts of an atom. Okay. And we'll apply these in our discussion of each of these concepts. So starting with atomic radius. And Lavanya, yes, repulsion between inner shell electrons and valence electrons. Perfect. Very good. Best tip for short answer questions is answer the question. I think it'd be obviously an endless list of tips, but actually answer the question. Read the action verb, whether it's describe, explain, evaluate. You actually have to answer using the specific verb and look at the mark allocation. If it's 3 marks, think of what those 3 marks are allocated to before you write your question response. That way you're actually most likely to score the marks that you need. If you write for a 6-marker response, 3 sentences, obviously goes without saying that's not going to get you the 6 marks. Okay, so atomic radius. Total distance from an atom's nucleus to the outermost occupied electrons. The way that the trend works, going left to right, is you will have a decreasing atomic radius as you go from left to right. The reason why is because every time you add an electron into the valence shell, so let's say we add an electron into this valence shell over here, this purple one, what we've also added into this molecule, into this element, is we've added an extra proton into the nucleus. So we have to ask ourselves a question in terms of ZF. So ZF equals the protons in the nucleus minus the electrons inside of the valence shell. First of all, has the proton number changed? Yes, our proton number increased. Has our shielding changed? Looking at all these inner electrons. No, we're still in the same shell. So what's happened is now the overall attraction of that outer shell is slightly stronger than it was before, pulling in your outer valence shell. Hence, your atomic radius decreases as you go left to right. So when you can explain these concepts in terms of your nuclear attraction and your shielding, that is where you get the marks. That's what the 3-mark, 4-mark, full-mark responses are getting, and why you may only be getting 2 marks when you think you should be getting 3. Going from top to bottom, it's a bit easier. You just say that each time you go down, you're adding an extra shell, and hence the atomic radius increases going top to bottom. That one's a bit easier. Questions in the chat. Are you allowed to draw a table when doing like a comparison question? Yes, but I would advise, unless the question has like a keyword compare, to not do it. And even so, full sentence dot points for me have always been my preferred mode of short answer. Bottom line is, as long as you're writing in full sentences that are clear, you can leave it in a format that would be understandable. For the Mod 3 and 4 workshop, that will probably go next week, potentially, if we have demand on another registration. And yes, that would be all the questions there. Okay. Where would the diagonal arrow go for it? Oh, right, okay. Diagonal arrow for atomic radius, sure. Your diagonal arrow is going to go this way in terms of increasing atomic radius, if you were to do it like that. Don't get why across the period atomic radius decreases. Going one more time to try explain it again. When you go from left to right, what you are doing is you are adding a proton to the nucleus. So let's say now we do it in orange for the next one. You add a proton to the nucleus, and you also add an electron to the valence shell. That changes how much positive pull your nucleus has in, because the nucleus is positively charged. So that's going to increase your Z, the nuclear attraction. And the shielding, which is all of the inner electrons, hasn't changed. It hasn't changed at all. So the net effect is your ZF, your effective nuclear charge, is increased, and your outer shell of electrons is pulled in slightly stronger than it was before. And if it's pulled in slightly stronger than it was before, that means that it will sit slightly closer to the nucleus, which is why every time you go one to the right, you are shrinking, because the protons in the nucleus are pulling stronger, whilst the shielding is not changing. And then you reach a point where you fill the valence shell and you add in a new shell. Massive increase in atomic radius all at once. And that's really what's happening with your atomic radius. Hopefully that makes better sense. Okay, cool. First, ionization energy. You use the exact same explanation. If you can explain in terms of ZF, this is exactly the same. Going left to right, as you fill the valence shell with more and more electrons, the nuclear attraction is also getting stronger, which means this valence shell is getting held tighter and tighter and tighter and tighter. It's very hard to now remove those electrons. So would it be easier or harder to ionize and remove an electron than it was before? And it would be, as you go left to right, it becomes harder. The ionization energy increases. And if you go top to bottom, you are adding in extra shells around the inner shells, which means you're pushing up your shielding significantly, and actually becomes easier and easier to remove electrons as you go top to bottom. So for your ionization energy, your trend goes from diagonal arrow, because it seems to be helpful. Your ionization energy will increase as you go left to right, and it will decrease as you go top to bottom, so it means increase as you go up. So your diagonal arrow would go this way for increasing ionization energy. Since ionization energy is how much energy is required to remove an electron. Could you explain how to answer questions that you have, like ionization energy removing 1, 2, 3 electrons, and you have to find the element and explain how? Yes, definitely, Naomi. So, the questions you have, the question will typically come where you have a sequence of ionization energies like these. So you'll see that ionization energy sort of increases following this trend going up until there's a massive drop in ionization energy from one atom to the next. They may not give you the atomic number, they may just give you the ionization energy, they may not even name any of the elements. And the other way they can ask it is they can ask you to find the valency of a particular element. So what is really important to note is when you have a big drop in ionization energy from one to the next, this means that you have reached the change from... This is when you now have an extra valence shell. A new one. A new extra valence shell for element number 11, because it's now much easier to ionize element number 11, which we know is sodium. So what that tells you is the element that came right before it on this graph is in group 8 or 18. The element that came before that is in group 7. The element that came before that is in group 6, 5, 4, 3, and so on. 2, 1. And from that, you can find the valencies. You would know that for group 7, the valency is -1, -2, and so on. And for group 1 and group 2, +1, +2, +3, so on. So that would be how you find the valencies. That's the first way they can ask it. And if they gave you one of these elements, for example, they do here, they give you neon, you can use the ionization energies to find the elements before it, after it, and so on. I think the classic one they ask is, there's two elements with two of these elements like X or Z make a compound together. This is their ionization energies, and you have to find their valency and then show the compound. One of the teacher's favorite questions. But if you understand, the big drop is the new valence shell that allows you to find valency. Okay, hopefully that's answered. And electrostatic attraction decreases. Depends on which trend we're talking about, but we could say that, electrostatic attraction being the nuclear the net nuclear attraction can be thought of as electrostatic attraction. I would say yes, and that would be a correct thing to say if we're talking about a decrease. How would you answer questions that ask you to refer to the graph? It goes without saying, you talk about the graph, and you would talk about the specific points that you want to reference. So you would say, for example, here, if I'm going to reference a graph, I would say the element at atomic number 3 and ionization energy of 5 eV, for example. Specify what you're talking about, the point. Atomic radius across period. No. Electrostatic attraction would increase as you go across... across a period, yeah. It would increase because you are holding onto the valence electrons tighter than before. So I would say it actually increases, not decrease. Okay, last property here. Electronegativity. I am wary of time. We still need to get through bonding. Electronegativity is going to increase left to right, and it's going to decrease top to bottom for the same reasons as before. This is our Pauling scale, which allows us to see electronegativity. And finally, reactivity with water. This talks about, there's several trends. I think this is lower yield. I'll leave this up on the screen. If you want to take a screenshot, go for it. But I want to move on to bonding. Okay. So, big topic, bonding. First of all, electronegativity, we have to understand what it is. If you know what it is, type in chat. How do you think about electronegativity? First thing. So, to me, electronegativity is how tightly an element or atom holds onto electrons. How tightly it holds onto electrons and draws it in from other elements as well. We can see that electronegativity is highest in the top right, with oxygen, fluorine, and nitrogen typically being recognized as our higher electronegativity elements, although chlorine also is very high. And why this is important for bonding is because how strongly an electron holds onto electrons dictates whether you're going to make an ionic bond, a polar covalent bond, or a non-polar covalent bond. A critically important number is 0.4. Really important number. Because when you compare two elements against each other, most importantly non-metals, if the difference in their electronegativity is greater than 0.4, that means it will form a polar covalent bond. If it's less than 0.4, it'll be non-polar. So let's take two examples. Something bonded to itself. Chlorine bonded to chlorine. 3.16, 3.16, reading off of the Pauling scale. The electronegativity difference is 0, hence this is a non-polar bond because it's less than 0.4. Then we can look at, say, chlorine to, let's do carbon to hydrogen because it's more common. 2.55, 2.2, difference is 0.35. Hence, this is non-polar as well. Carbon to oxygen, 2.55, 3.44. Difference is 0.89. This is now polar. And that classification is very important because then if you can't do this, you can't figure out if a molecule overall is polar or not. And this may be the start of your problems. If you have difficulty finding out whether a molecule is polar or not, that would be where you go. Great question. How do you know the numbers during a test? Typically, they'll give you a Pauling scale, or they give you certain electronegativities for specific elements. But if they don't, and this is the, I guess, year 12 understanding you get from us at Catalyst early, is if you have, these are really only the important polar ones that you need to know. If you have a carbon or a hydrogen that is bonded to any of a nitrogen, oxygen, fluorine, chlorine, or bromine, any of these 10 bonds, that is a polar bond. You don't need to know the numbers, you can just remember that. Carbon and nitrogen, carbon and oxygen, carbon, fluorine, carbon, chlorine, bromine, any of those is going to be a polar bond. That is your hack. And if it's not one of those, for the most part, it's going to be non-polar in a HSC context. In fact, pretty much always is going to be non-polar. A few questions. Could you do NaCl? Yes. NaCl is going to be sodium, and I'm getting these numbers from the Pauling scale here. This is where I'm drawing all my numbers. NaCl would be 0.93, Cl 3.16, hence the difference is massive. It is in fact 2.23, which is greater than 1.8, and it does form an ionic bond. I think the rule for ionic bond is not always so hard and fast, so the more important classification is for polar covalent versus non-polar covalent. And now I'm not sure what you mean by using Schrodinger's model. If you want to explain that, that'd be cool. But yes, we've talked about ionic and covalent compounds. We won't talk about it too much. Ionic compound, metal, non-metal, donation of electron, whereas a covalent compound, sharing of electrons. We know about valencies already, and we've talked about nomenclature at the very start of today. It's bent, it's polar because unbalanced. That's a little bit different. That's molecular geometry. We'll get into that in a second. We need to be able to do Lewis dot diagrams. So you have dot diagrams for covalent compounds and ionic compounds. They are different. An ionic compound dot diagram shows, and before I go into that, any dot diagram will obey the octet rule in a HSC context. So you have to have 8 valence electrons around the atom in order for it to be considered stable. For an ionic compound, you have square brackets around each atom, and you show the electrons that were once around a metal to have been donated to the non-metal. So in this case, the sodium has donated its electron to the chlorine. That is why it gains a positive charge. It has lost an electron. And the chlorine will gain a negative charge because it gained an electron. And now they attract each other in the ionic lattice. If you want to show something with a 2+ or 3+ charge, you just show several chlorines around that cation. For covalent compounds, you do the same. You have to have an octet. That's the thing that's the same. But the difference is you have a sharing of electrons, which means you can essentially use a neighboring atom's electrons to make up the octet. In this case, we have carbon dioxide. This oxygen has shared 2 of its electrons with carbon, giving it 8. This carbon has shared 4 of its electrons, 2 with each of the oxygens, and this oxygen on the right has shared 2 of its electrons with the carbon in the middle. So now each of these elements has 8 electrons, which is why it is now stable. Have a go at some of these if you're uncomfortable with dot diagrams. And then this comes onto the idea of molecular shape. So molecular shape, there are 3 main shapes you need to know. If you know the 3 shapes I'm about to say, go for it. It's the main configurations with just bonds. So if you have 4 bonding groups around a covalent molecule, you'll get this. If you have 3 bonding groups, you'll get this. And if you have 2 bonding groups, you'll get this. Each of these has a name. This is tetrahedral. This is trigonal planar. And this is linear. So, tetrahedral, trigonal planar, linear, these ones form because of a special rule called special theory called the valence shell electron pair repulsion theory. What that means is that the bonds will repel to the maximum angle apart in each of these, since these bonds are all consisting of electrons, which will repel apart. These 3 geometries allow you to then find the other geometries, which are just simply where you have one of these bonding groups replaced by a lone pair. So that would mean you can get a tetrahedral with one of the bonding groups replaced with a lone pair, or you can get a tetrahedral with 2 of the bonding groups replaced with a lone pair. This is called a trigonal pyramidal. This is called a bent structure. You can get the same with the trigonal planar. Trigonal planar over here. If you replace one of the bonds with a lone pair, guess what? This is also called bent. Any structure where you just have one bond, for example, you have a linear that got replaced by one of the bonds replaced by a lone pair, this is still called linear. So if you just have one bond and all lone pairs, otherwise it's also referred to as linear. And those are your different molecular shapes. Okay, some questions. SO2 is a harder one, definitely. I'll probably leave that for today just because we have to get through the rest of bonding. You will not get this document. All Catalyst students have access to our notes, but we can't just send our notes out, otherwise it wouldn't entirely be fair. You can get access to the first session if you submit the resource form on our website. That will get you the first part for free, but otherwise the rest of the notes are reserved for our students. The shapes, yes, you do need to memorize these. I would say they're important, in fact, crucial. So you need to know the shapes, so the foundation ones, tetrahedral, trigonal planar, linear, as well as the ones with lone pairs, and you need to know the bond angles. The bond angles are 180 degrees, 120 degrees, 109.5 degrees. You need to know those. Is H2O bent? Yes, H2O is bent, because H2O has 2 lone pairs and 2 bonds, hence it's bent. And you know that now because of your understanding of the geometry. And yes, Catalyst is fully online, so we teach on Zoom every week, weekly sessions, 9 sessions a term. We teach 3 to 5 weeks ahead of class pace. Basically this, but slower because you learn it the first time, and you learn it 3 to 5 weeks ahead of your class space. You know exactly what's going on when you step in the classroom. When does it get replaced by a lone electron pair? So it's not, replaced for a molecule. It's not like you're changing one thing out for another. It's as if you have a different molecule that has instead 2 bonds and just a lone pair. That would be how you get different configurations. So we're talking about different molecules have different numbers of bonds and electron groups, bonds and lone pairs around them, and that gives you different shapes. No worries at all, Mahathi. It's the least that we can do. Okay, I think that's all the questions. So per class, we keep our class to single-digit numbers, and I think on average we're about 6 per class. So we run pretty small classes, meaning you get the attention that you need when you have questions, when you're unsure. We can go back on things. Okay, cool. Allotropes, I'm wary of time. I'm going to skip this because this is just theory. Take a screenshot if you want. Summary is allotropes are elements that exist in different states. So you have diamond and graphite as your best examples. Know the differences in their structures. These are case studies your teacher can ask you on specifically. Don't leave yourself bare with this. Allotropes are here. Okay, but finally, we get to chemical structure, and after that, we get to bonding with the intermolecular forces. Very quickly going through the structures, because I think you guys should be all over this. We have ionic networks, covalent networks, metallic structure, covalent molecular structure. Ionic networks, as we know, anion, cation, properties are shown on the screen. You should be able to talk about melting point, boiling point being high. That they're hard but brittle, because when they get misaligned, the whole lattice essentially aligns with positive next to positive and negative next to positive. Sorry, negative next to negative, and the whole thing shears apart, which is the property of being brittle. They're not conductive because there's no free electrons or ions moving around. They are not similarly, or not similarly. On top of that, if you were to actually melt down an ionic lattice and break apart the ionic bonds, you now have free moving ions in a liquid. So that is why molten ionic compounds are conductive electricity, but solids are not. Covalent networks, as we sort of just quickly breezed over, these are covalent bonds through the whole network. They are not molecular, and they do exist in lattices. That means that they have strong covalent bonds holding together everything, so they do have high melting point and boiling point. They are also hard, also brittle, because if you break them, they tend to shear apart, and they're not conductive apart from graphite. Graphite is the only example of this that we have in our syllabus. So if you have a covalent network, all the electrons are held up in these covalent bonds. So there's no free moving electrons. The atoms themselves are neutral, so there's no charge. Graphite is a weird example because it has delocalized electrons that float between the sheets of graphite. So that means when these electrons can move around, that makes graphite conductive, but no other covalent network has that strange property. It's an exception. Metals, we know about the high melting and boiling point because of the strong electrostatic attractions between the metal cations and the delocalized electrons. They're hard, but they are malleable and ductile, meaning that you can hit them into flat sheets, malleable, or you can hit them and stretch them into wires, being ductile. This is because you have the delocalized electrons around the cations, which essentially means that the shape can move around freely, form new shapes, and still be holding itself together. They're also conductive of electricity and heat as both a solid and a liquid, because if you have solid metal, these delocalized electrons, as we've shown before, these delocalized electrons are free to move around everywhere. That is what's giving it its conductive property, the electrons that are able to move around. And heat conductivity, similar idea, but it's just that if you have stuff that's able to move around the structure freely, you can then propagate heat through the structure as well. And finally, covalent molecular, and this will tie off the end of the session with our intermolecular, intramolecular bonding discussion. Covalent molecules are individual entities. This is the most misunderstood concept, I think, out of all of this. So if we talk about a water molecule, it is an individual entity with lots of other water molecules around it. When we talk about intramolecular bonding, intramolecular bonding is talking about the covalent bond that holds together a covalent molecule. Intra, within the molecule. Intermolecular talks about between molecule forces. Intermolecular. So this water molecule has intermolecular forces with other water molecules. And if you know the forces that exist between water, type them in the chat. Test yourself. Because when you actually melt or boil molecules, and let me be entirely clear, when you melt or boil molecules, you are breaking apart intermolecular forces, not intra. You do not break apart covalent bonds when you're boiling or melting a covalent molecule. You are breaking apart intermolecular force. So you're breaking apart the hydrogen bonding, the dipole-dipole, and the dispersion, which exists between each of these molecules. All of those three forces, intermolecular forces, exist between these water molecules. And when you boil or melt, you are breaking them apart. Okay. And once again, they're not conductive, no free ions or electrons to carry charge. Quick summary. And we'll finish off on intermolecular force. So here we go. Intermolecular force. Oh, hang on. Questions. What was the positive and electron diagram of? Oh, this is metal. So this is a metallic structure where you have cations surrounded by electrons. Would it be all three because hydrogen bonds dipole because it's polar and dispersion because every particle has it? Yes, perfect. I don't know what your name is, Purple Bookworm. What Purple Bookworm has said is 100% correct. So as we get into the next part, the final thing that I want to talk about today is how do you know whether you're going to form each of these intermolecular forces? And the first thing you need to understand is that we find it out by figuring out whether a molecule is polar or not. A molecule is polar if it has a polar bond and it is unsymmetrical. So having a polar bond, as I said before, it's any of carbon or hydrogen bonded to nitrogen, oxygen, fluorine, chlorine, or bromine. Any one of those 10 bonds means you have a polar bond. So if you have that, you say tick, move on to the next criteria. You then also have to have a molecule that is unsymmetrical rotationally. So, one molecule here. Carbon with 4 fluorides around it. And nitrogen with 3 hydrogens and a lone pair, ammonia. Which of these two molecules is polar? One of them is polar, one of them is not. Which one is polar, which one is not? Type in chat. Quickly going back. Diagram above that. Oh, this one. This is also metal. This is the same thing. Cations surrounded by electrons around it. It's also a metallic structure. Yes, so every molecule has dispersion force. Every molecule has dispersion force. And then dipole-dipole only comes about when you have a polar molecule, which we're about to figure out how to find. So yes, ammonia is the polar one. And the reason why it's polar is because it is unsymmetrical. It means that since nitrogen is a highly electronegative element, it pulls electrons from the hydrogens in towards itself. So that means you aggregate electrons around the nitrogen, giving it what we call a negative dipole. A dipole is a partial charge. And because all these hydrogens had their electrons pulled away, it means that these will now gain a positive dipole. And this only creates a polar molecule because the whole thing is unsymmetrical. The top half is now overall negatively charged. The bottom half is now overall positively charged, meaning if something else comes along with dipoles, it can attract or repel it. Looking at the other case, carbon tetrafluoride, this is not polar. It has polar bonds, but it is a non-polar molecule. And understanding this is going to save you at least a mark in your prelim. Every exam will have it. Fluorides, again, these are the electronegative elements. They all want to pull electrons from the carbon towards themselves. However, because they are splayed apart at perfectly equal angles, all of this pulling of electrons get perfectly cancelled out, and you end up with no dipoles at all. So for a molecule that is rotationally symmetrical, so that means if you move all the bonds into each other's positions, it looks exactly the same. If that's the case, the pull on electrons all cancels themselves out. And this would in fact be a non-polar molecule, despite having polar bonds. So the importance of that is once you are able to find out polarity, you're able to say what intermolecular force any given molecule has. Intermolecular is not always polar. Intermolecular, and this is why we're trying to find the polar one. Because intermolecular forces, as we said, there are three main ones: dispersion force, dipole-dipole, and hydrogen bonding. The line that I like to draw is right here. Right here. Between dispersion and dipole-dipole. Everything has dispersion force. Everything that has electrons is going to have random electron dispersion moving around, forming temporary dipoles. But only something that is polar qualifies for having dipole-dipole or hydrogen bonding. So if you can identify a polar molecule, you can say that that molecule has dipole-dipole interactions. That is why it's important. And that's going to come up in MCQ, it's going to come up in a short answer, I almost guarantee it will be in your exam. So if you can talk about why a molecule is polar, and then talk about that's the reason why it has dipole-dipole, that's saving you a mark or two already. So, the final barrier is then when do you form hydrogen bonding? Hydrogen bonding forms if you have a nitrogen to hydrogen intramolecular bond, an oxygen to hydrogen, or a fluorine to hydrogen somewhere in your molecule that qualifies it for hydrogen bonding. So, that would mean water can form hydrogen bonding between its oxygen and hydrogen, since these are the most polarized or most polar bonds in existence. They create the biggest, strongest dipoles. Great Anam and great Manathi. That is correct. So that's why water forms hydrogen bonding, but hydrogen chloride doesn't. Hydrogen chloride would just form dipole-dipole and dispersion, but not hydrogen bonding. CH bond is nonpolar, correct. Okay. And the hierarchy of strength is therefore dispersion, dipole-dipole, hydrogen bonding. And applying that to your melting point and boiling point discussion, the stronger the intermolecular force for a covalent molecule, the more energy is required to break it apart. And if there's more energy required to break it apart, that means you have a high melting point and boiling point. That's what you talk about in your exam. And with that, we will leave it there for Module 1. We've made it through. Took a little bit longer than intended, but we've gotten through. If there are any questions, feel free to chuck them in the chat as we finish up here. As a quick final reminder, for those who aren't staying with us for Mod 2, our program for Year 12 starts in just under 3 weeks. So we're going through Mod 5 or Mod 7 if you're going in a weird order. If you're keen to get teaching like this, basically get shoved ahead of your class pace and learn so quickly and comprehensively that you can't possibly do badly, basically submit a form on our website, say you're interested, and we'll give you a call to see if it's the right fit for you. We have opened a few new classes, and it'll be pretty much starting up, as I said, September 22nd. Similar format to this, 9 sessions in the term, learn 3.5 weeks, 3 to 5 weeks ahead of class pace, step in class, know exactly what's going on. So, questions, leave them in the chat. Otherwise, I'll take a quick breather myself, and I'll see you back for Mod 2. No worries at all, Will. Glad it was helpful. And yeah, if we've been able to cover this much in 2 hours, imagine what happens inside the program. No worries at all. Anam, Purple Bookworm. No worries, Mahathi. And Anam, we're not skipping Mod 6. It's just that some schools do Mod 7 first, and then they do Mod 8, and then go back to 5 and 6. Or they do Mod 7, then 5, then 6, then 8. So we offer a Mod 7 program in case people want to do that. And we would just do Mod 6 in either Term 2 or 3 if you do Mod 7 first. Mod 2 is at 11. We're going to start in 5 minutes. Maybe we'll do 11:05. Give us a bit more of a break. I'll leave a comment in the chat just so we have it. Mod 2 starting at 11:05. Pricing for the programs on the website. So if you go through the courses, you can have a look and see what the pricing is. Otherwise, if you just want to have a chat to one of our team, submit the form and we can take you through what's inside and also the pricing on a call. Find it's a bit nice just chatting to someone. Okay, cool. I will take a quick break. See you back in just a second. If you can't join Mod 2 now, they'll be recording up probably later today once YouTube finishes buffering this massive session. No worries at all, Lucy. Okay. We'll get started at 11:05. A few questions in the chat I'll just get to quickly. What else do I need to know in Mod 3 other than like all the equations such as synthesis and galvanic cells? Yeah, Mahathi, as you say, oxidation reduction. Obviously, that's the main part of the module. But other than that, also metal reactivity. I think that's a commonly overlooked part of the module. So you need to know your metal reactivity experiments that allow you to prove whether one metal is more reactive than another. That's a big part of the module too. But otherwise, yeah, galvanic cells is probably the main thing. Yeah, I'd say as the one thing I'd say not to forget about metal reactivity. That jumps out. And can we make a reel on the most frequent questions that come in Mod 2 and 3? We almost certainly can. We'll do that over the next few weeks. So we'll do some, ideally this coming week. They should be coming out as we go along. Do we have to memorize the reactivity series? No, do not memorize the reactivity series. You have it somewhere that you can just reference. Where can you get it? There's a special place where you get the reactivity series. And you'll get that in your exam. Gia, can you focus more on limiting and excess questions? Yes, we can do that for sure. Although today we probably won't be able to do in-depth questions just because we're going over content more so. I'll talk about the concepts, but it won't really be doing lots of questions. That's something more for your own revision. Yes, Mahathi, the reference sheet. So the reference sheet will show you, and I'll pull it up just so we can have a look. Reference sheet. Oh, lots of writing. Standard potentials. This is effectively your reactivity series for your purposes. At the top, this is most reactive. As you go further down, it becomes less and less. How do you memorize solubility rules easily? Nag, Sag, PMS, Castro Bear is the easiest way. Yeah, exactly, Mahathi. That's what I do. Nag, Sag, PMS, Castro Bear, and that just basically means that for any of nitrates, acetates, group 1, sulfates, ammonium, and group 7/17. Oh, hang on. No. Wait, why am I blanking? What's the second G? Anyway, I'll work on PMS. PMS, Castro Bear, lead, mercury, silver, and then calcium, barium, strontium, barium. You would be able to figure out that any of those on the left, the soluble salts, are going to be, yeah, it is group 17. Any of these on the left are soluble, except when they're bonded to one of the exceptions. So if you have, for example, lead sulfate, actually I should specify where the exception is. Sulfates, when bonded with either of PMS or Castro Bear, or group 17, when bonded with PMS, these will be insoluble. So what that means is for sulfates, if I have calcium sulfate, that's insoluble to some extent. Lead sulfate, insoluble to some extent. But if I have, for example, let's say magnesium sulfate, that's not one of the exceptions, this would be soluble. And similarly for group 17, barium chloride, it's not one of the exceptions, therefore this is soluble. Hang on, barium chloride, yes. It's not one of the exceptions, so it is soluble, yes. But if you had silver chloride, AgCl, that is one of the exceptions. That would be insoluble. So that would be how you'd work through your PMS Castro Bear. Okay. Will we be doing this for Mod 3 and 4? For the Catalyst students, we're running it tomorrow, 9 a.m. and 11 a.m. And that'll just be on our Zoom. That's closed off, unfortunately. But next week, if you're not for free. Cool. So, to quantitative chemistry, we're going. I'll do a quick sum of what we do again. Just getting one that we are getting some buffering. If I can. Loading. That's mileage. Okay, is this better? Checking in with everyone. Is this better? Yes, no, yes, no. It looks better on my end. Okay, cool, great. Let's get going. Sorry about the delay. So, Mod 2, as I said just before, we've got quantitative chemistry, lots of important concepts in here. Truth is that the revision for this module really is going to be more even more so than Module 1, is more question-based than anything. Yes, we can go through the concepts today. This will give you a broad overview of everything, but you have to do questions. You have to put yourself in the deep end, do a ton of corrections before your exam. and let's just get straight into it. So starting us off with the first inquiry question, we have chemical reactions and stoichiometry. So we need to know, first of all, about the law of conservation of mass and how that gives us the concepts of stoichiometry, and I guess later on how it ties in with molar stoichiometry as well. Law of conservation of mass. Matter cannot be created or destroyed, which means that when you perform a reaction, the mass of your reactants will be equal to the mass of your products. That will always be true, no matter what. And so that gives us then this idea of, within any reaction, there's a ratio between the parts that exist. And that idea of ratios between parts, that is stoichiometry, which is just that. Ratios between parts. So, we have in this reactions sodium reacting with chloride to make 2 sodium chloride units. We can see that there's a coefficient in front of each of these, and when we talk about stoichiometric ratio, it's talking about the ratio between each of these parts. So 2 to 1 to 2, we should know this by now. We should also be able to balance chemical equations, as I said before. And talking about definite composition, a compound will always contain the same elements in the same proportion by mass. So CO2 will always be 27.2% carbon, oxygen will always have 72.8% of it by mass, given that CO2 is its formula. So going back to Mod 1, the first calculation we should be able to do is our percentage composition, as well as our mass composition using a percentage composition. Formula's up on the screen. I won't spend too much time here, as it's relatively straightforward. So you should be able to find from given masses a percent composition, and from a percent composition find how much mass of a component exists within a substance. Okay, you should also be able to talk about density. Is the audio breaking out? Can everyone hear okay? Or is the audio funny? Is the audio fine? I feel like the lag's gotten bigger. Okay, well, I'll keep going for now. Okay. Yep, I got a message. I think the lag is now about 30 seconds now. Alright, we'll keep on going. So, mass, density, you should be able to talk about density as a formula where density is equal to mass divided by volume. You can think of density as, for the amount of space something takes up, how much does it weigh? If it weighs more for a certain amount of space, so say this charger brick, I would say is like somewhat dense. If I pick up a volume of, let's say, a volume of, what's something good? I don't know, volume of feathers at the same size. It's going to have a smaller mass but take up the same volume, hence its density would be less. So your density, function of mass and volume. The units, therefore, are in terms of mass and volume as well, grams per mil or grams per liter. That would be your typical units for density. Convert from volume to mass, mass to volume using density. Here are some questions to practice if you haven't done so already. And the answers below. So, we won't worry too much about the prac. Moving on to the concept of the mole. We understand what a mole is in this module. A mole, type it in the chat if you know. A mole consists of a very big number of something. A mole is a counting unit. So if you say you have a dozen of eggs, you would talk about a mole of something in the same way. A dozen being 12 of something, a mole meaning you have 6.022 times 10 to the 23 of something. And it's a useful counting unit to quantify massive numbers of substances. So, of substances, molecules, whatever it might be, atoms. Otherwise, you're going to be counting for a very long time in smaller units. So, a mole consists, the formula for a mole is the number of particles divided by Avogadro's constant, which is exactly that number, 6.022 times 10 to the 23, that allows you to find the moles. There's also another formula for mole, which involves the molar mass, which we talk about in a sec, and that is pretty much all we need to know about the mole for now. We also know that if we have one atomic mass unit, if you have 1 mole of something that weighs 1 atomic mass unit, it will weigh 1 gram. So 6.022 times 10 to the 23 atomic mass units is a gram. Okay, some simple conversions. These shouldn't be too problematic by this stage of the year. And then you get into molar stoichiometry. So for any equation, when you talk about any of the substances you can talk about, let's say you had 7 moles of H2 gas. Molar stoichiometry allows you to relate the moles of one substance to another because they will react in ratio. So if you have even simpler, starting it with just 7 hydrogen molecules, it would take 3.5 oxygen molecules to fully react with those 7 hydrogen molecules. This can be expanded to then double. Say you had 14 hydrogen molecules, you would then be able to react 7 oxygen molecules. You can then expand this to 6.022 times 10 to the 23 times bigger, and you could say that, hang on, if I have 14 times 6.022 times 10 to the 23 hydrogen molecules, and I have 7 times 6.022 times 10 to the 23 oxygen molecules, they will react exactly in the right ratio as well. So that final step allows you to say, therefore, if I have 14 moles of hydrogen, I'll be able to react it with 7 moles of oxygen in a 2-to-1 ratio. And that's pretty much what we need to know about molar stoichiometry. We can compare moles across a equation based on the coefficients. What we cannot do in any case ever is say we had 7 grams of hydrogen. We cannot say, absolutely not, we cannot say that we will react 3.5 grams of oxygen. That is very wrong. You have to convert these into moles to find the answer to that. We'll talk about that type of calculation later. It's called a mass change. Okay. So, that's moles, the concepts behind it. There's some questions here if you want some to practice, but just to introduce those ideas first. Any questions in the chat, chuck them in. For those who are new, joining just now, feel free to ask questions whenever. I'll get to them when the stream catches up to the chat. Okay, so there are then 5 main calculation types that you need to know in order to get through your mole calculations. There are your simple mole and mass calculations. I rate this on a scale of easy. Percentage composition, I'd say that's easy. Empirical formulae, I'd say moderate. And the extension of empirical formulae, a lot of people don't know, is you can also be asked to find molecular formulae, which I'd say is veering towards hard, but also still moderate. I'll keep it in purple. Solving problems regarding mass changes, I'd say is moderate once you know how. And even limiting reagent, once you get it, I'd say it's moderate, but this is the hardest of the lot. So hard/moderate, depending on the question. When things get difficult, it's when they combine this concept, or one of these concepts, with a concentration, or a dilution, or they combine it with a gas law, for example. Your calculations aren't going to be hard in isolation. It's only difficult when your teachers combine concepts together, which they should if they're writing a good paper. So, we know what a mole is. First calculation type, molar mass. Moles equals mass on molar mass. Simple, and it allows you to convert between mass and moles. You should be able to do this on automatic by this point. If you want a visual way of doing it, you have your molar mass pyramid. You can always use that as well. Units for molar mass will be in grams per mole, kilograms per mole, or whatnot. Percentage composition. Percentage composition, as we've said before, these are questions where you get told a mass of a substance and the total mass, and you have to find the percent composition. Nothing too crazy. Or you get given where's an example? Yeah, or you get given a total mass and you have to find the percent of one part. The harder way that they can ask this question is they simply, without giving you any of that information, they ask you to calculate the percentage composition of one substance in a compound, such as potassium dichromate. This question type, your approach is to assume that you have 100 grams of this substance. That's one way you can do it and solve it that way. Or you can just take the molar masses and solve using them. So if you take the molar mass of potassium, chromium, oxygen, and you sum them up to give you the total mass of potassium dichromate, it's just an added step. You just have to find the molar mass yourself, and you have to find the molar mass of the component. So chromium being 52 grams per mole, the total molar mass being 294.2 once you sum everything up, including the counts of the different parts. And that would allow you to find the percentage composition, placing the molar mass over the total molar mass. Very common question type. You then also have your empirical formula questions. So you should know what an empirical formula is. You should know that it is the simplest whole number ratio of elements in a compound, whereas a molecular formula represents the exact number of atoms present. So N2O4 is molecular formula for this molecule, and it can be simplified into an empirical formula if you just want to show the ratio of parts. So NO2 being the empirical formula there. Similar for the other two molecules shown here. Okay. As a test, everyone comment in the chat what the empirical formula for glucose is, and I will say it's correct once it comes up in the chat. Okay. The question you're actually going to get asked in your exam, though, is something that reads like this. You get asked for a compound that contains 40% carbon, 6.7% hydrogen, 53.3% oxygen by mass. Determine the empirical formula of the compound. Exceedingly common question. Exceedingly common. All you have to do here, all you have to do here is assume that you have 100 grams of your compound. Assume you have 100 grams. It's the first thing you do. That then allows you to find a assumed mass of each component. So if you have 40% carbon, it means you have 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. You can assume any mass you want, but 100 makes it easy because it can be directly translated across for the percentage compositions into what masses they actually have. Then, once you have these masses, divide them all by their molar mass, because that allows you to then put them into their mole amounts. As you can see here, 3.33, 6.66, 3.33. That is now the mole amounts we have of each. And that can now be related in terms of their molar ratio by dividing by the smallest mole amount. Gives you a 1 to 2 to 1 ratio, and we therefore know that the empirical formula of whatever this is, this compound, is CH2O. And everyone who has just typed in chat on my screen CH2O, I know there's a bit of a lag. Yes, that is the empirical formula for glucose. And as a matter of fact, this molecule here could be glucose, the one we just talked about for the empirical formula. It could be glucose, but we don't know. It could be C2H4O2. It could be C6H12O6, glucose. It could be any expansion of this empirical formula in a different ratio. The only way, and this is the extension, that we can find what molecule it is if they give us a molar mass. And this is your finding molecular formula archetype question. So if you get asked this question, same stem, the only thing they add on top is a molar mass. And they say, instead they ask you for, not empirical formula, they ask you for molecular formula. You will do the same steps to arrive at the empirical formula. So everything you did before, you arrive at this. So all of this work you have to do to get to this point. Find the empirical formula CH2O. The final step is then using the molar mass, you can find out how much CH2O fits within the total molecule. Because you know that the molar mass of the whole molecule is 180, you can find the molar mass of CH2O, the empirical formula. So adding up a carbon, 2 hydrogens, 1 oxygen, you get 30.026. And you can find the ratio between the empirical formula and the molecular formula. In this case, it ends up being about 1 to 6, which gives you a ratio, or it tells you that your molecule is 6 times bigger than your empirical formula. Therefore, this molecule actually is glucose. And that's how you would find it out. You need a molecular mass. Question in the chat, for empirical formula, sometimes they ask to find the unknown element. Can you please go through those types of questions? I think I need a specific question to go through, because I know what you mean, but I'd need a specific one. Otherwise, I'd just be writing up a question for some time. So if you have a specific one, feel free to comment it and I might go through it at the end. But otherwise, here are some molecular formula questions, what you can expect, and some working. I think that is all. Okay, 2 down. Third one, mass change. Mass change is also exceedingly common. And it is the question type where you get, I just go to an example. Question type where you get a mass, 12.5 grams of sodium, for example, and they say that there's a reaction where you go react sodium and oxygen to make sodium oxide. They ask, how many grams of sodium I need to produce 12.5 grams of sodium oxide? Sorry, I misread the question slightly. 12.5 grams of sodium oxide, how many grams of sodium are needed? The mass change is needed because you can't just say that 12.5 grams of sodium oxide will be formed from 25 grams of sodium in a 2 to 1 ratio. That is incorrect, because you cannot compare masses in molar ratios. So a mass change involves changing the initial mass to a mole amount, relating the mole amount using a ratio, and then turning the mole back into a mass. Hence, it's a mass change. A mass change. And that will then give you your sodium mass by the end. And the working is shown here. So what they did is they turned the sodium oxide into moles, 0.2. The moles of sodium can be doubled to find the moles of, sodium oxide moles. The moles of sodium oxide can be doubled to find the moles of sodium. And to find the mass of sodium, you multiply by molar mass, 22.99, to get back to 9.27 grams, your final answer. Again, some practice questions. I won't go through too many of these, just because we need to get through everything. Okay. I won't go through the questions just because we need to get through all the content today. But if you want to have a go at the questions during time, feel free. Isabella's... Okay, I'll have a go at that question at the very end today, if we have time. And Mod 3 and 4 Rap Review students reviews, yes, they're on tomorrow, 9 11 a.m., but they're closed for just Catalyst Chemistry students who are enrolled already. So that'll be on tomorrow. But if there's enough registrations on upcoming posts on our Instagram, we may run Mod 3 and 4 next week for you guys. So keep an eye out for that, and when it does come up, send it to your friends. Okay, so where were we? We just did the, mass change. Final question type. Limiting reagents. This is very important. Maybe we'll do a question for this just because of how important it is. Limiting reagent questions are important because when you react any two substances together, chances are you will not react both to complete. Like, you will not react both parts completely. There'll be one part that gets fully reacted and one part that gets left behind, a little bit of excess. And so the limiting reagent idea is that if you react two substances, as we said, you will always have a substance that is limiting, that once it runs out, the reaction stops. You will also have a substance that is left in excess, hence excess reagent. And the yield is how much product you form based on how much limiting reagent you react. So in this example, simplified down, hot dogs and buns, 5 hot dogs reacting with 4 buns as a model. Hot dog reacts with this one, this one, this one, this one. At that point, you've used up all of your buns. You have 1 hot dog left in excess, which is your excess reagent. Your buns are the limiting reagent because they ran out first. And your yield is 4 fully formed hot dogs as your product. So, this is the idea that underpins limiting reagent calculations. Your steps to do a limiting reagent calculation, always the same. Get your chemical equation. You need this for your mole ratios. So don't skip it. And oftentimes in prelim, it's worth a mark. Just have your equation no matter what. Don't leave anything to chance. Secondly, determine the moles of all your reagents. So turn them into moles by dividing by molar mass. Based on the mole ratios, determine which is limiting. So take the mole amounts and divide by, or multiply or divide by the mole ratio and figure out which one will exhaust first. And finally, use the number of moles of limiting reagent to discover moles of product. Welcome back, Kaylin. So as a quick example, before I maybe let you guys have a go at one, we have... Actually, no, you know what? Yeah, okay, no, I already showed the answer, it's fine. So we consider the respiration process a prevalent chemical reaction. We have glucose reacting with oxygen to make CO2 and water. So respiration. What amount of excess reagent is left over and what mass of carbon dioxide is produced in a reaction between 25 grams and 40 grams of oxygen. So this will go through how we find the limiting reagent. This will go through how you find the excess reagent as well, because it's asking about excess reagent left over. It's also asking about the yield. So we're finding 3 things. The limiting reagent, what it is, and using the limiting reagent, we can take that to find excess reagent. We can take that to find our yield. So, reaction's been provided in this case. the first thing we can do is turn our reactants into moles. So we turn the oxygen, so I'm looking down here at the green text, the oxygen reacted, we have hang on, 0. Hang on, no, I have to go back to start. Sorry, look at the steps. So the reaction equation is provided. Using the molar mass of glucose, you can find the mole amount by dividing by the molar mass, 180.06, and you can find that by adding up all of the atoms. So 25 divided by the molar mass gives you 0.1388 moles. For oxygen, the molar mass is 32. You do the same. So 40 divided by 32 gives you 1.25 moles. So you have the mole amounts of both of your reactants. You also have, from your equation, you have your mole ratio 1 to 6. 1 to 6. And you can now find out which is limiting. To do so, I always find it's easy to just multiply. You take the component that has the smaller part in the ratio, so glucose being 1. You would take this number of moles and multiply by 6 to see what number you get. The number that you get is going to be smaller than 1.25. You guys can test it out. It'll be about roughly 5.5-ish, something like that, 5.4 or 0.54, I mean. Or the other way you can do it is you can take the oxygen moles and divide by 6, which gives you how much glucose would need to be reacted to fully react that oxygen. And that number is 0.208. In either case, what you're doing is you're comparing that number against the other part, and you're seeing whether it's bigger or smaller. So 0.208 is how much glucose is needed to fully react 1.25 mole of O2. That is what that number refers to. And in this case, because we see that the moles we have is less, it's less than the moles we need to fully react oxygen. It means that the glucose will run out first. Therefore, glucose is the limiting reagent. That is the first step to any limiting reagent calculation. You have to find which part is limiting. Okay. I would say this question is probably, if it actually asks both of these parts, it's probably in the 4-mark range. So I'd say 1 mark equation, 1 mark finding limiting reagent, 1 mark to 1 mark to find the amount of excess reagent left over, 1 mark to finding the mass of carbon dioxide. Probably 4. You can make an argument for 5, but I think 4 is probably fair for this question. If it was just asking one of these parts, probably more 3. But it's asking for 2 parts. So, then, once you have your limiting reagent, you can find 2 things. You can find, first of all, the first part, which is asking about how much oxygen gets left over. So to find the excess reagent, you need to take how much was present in the first place and subtract how much got reacted. So to find excess reagent, excess amount equals total minus reacted. So in this case, we have the amount of oxygen reacted being 6 times the limiting reagent, glucose, because it's a 1 to 6 ratio. Therefore, you will react 0.83328 moles of oxygen to react all this glucose fully. To then find how much is left over, you take the total oxygen, subtract the reacted oxygen, which gives you 0.41672 moles. And that's your answer to the first part, how much excess reagent is left over. And they ask amount, not mass. For the second part, they ask what mass of CO2 is produced in a reaction between 25 grams, between the reactants, basically. To find this, you once again need to use the limiting reagent to find how much CO2 is formed. Because it's also in a 1:6 ratio, similar to glucose to oxygen. So for every 1 glucose mole you react, you will form 6 CO2 moles. That would mean that you are going to make the same mole amount of CO2, 0.83328, the same, 83328, and to find the mass of CO2, you simply multiply by the molar mass of CO2, which is 12.01 plus 2 times 16, giving you 37 grams of CO2 as your answer to 2 sig figs. And this brings up an interesting concept. Significant figures. What is the rule? Type in chat. Type in chat, what is the rule with significant figures, and I'll come back to it once we catch up. So limiting reagent questions. Let's do one of them. I think it's probably worthwhile. Let's have a go at the first one up here. Yeah, let's do number 1. I'm going to put a timer on. I'd say this is probably probably 3-mark question. Three marks. And I would say in an exam setting, you have 1.8 marks a minute usually. I like to stick it to 1.5, but we'll do 5 minutes on this question. So at 11:51, we will go through it. Everyone have a go. You're due at 11:51. Yes, correct. Smaller sig figs in the question, going back quickly. That is what you leave your answer to. So in this question, the least sig figs is 2 and 2, and 25 and 40 grams, which means your final answer will be left to 2 sig figs. That is the rule. So the significant figures left to the least significant figures in the question stem. And they have to be numbers you used. So if there was a temperature, for example, it was like 1 degree Celsius. It's not going to be like this, but if you had a number that was 1 degree Celsius in the question stem as well, they said it was 1 degree Celsius, but you didn't use it in your calculation, that doesn't get factored into your least sig figs. Actually, because you guys will be lagging, let's make it 11:53. A little bit more time. Okay, and when you get your answer, type it in the chat. I've got an answer from Anam. Oxygen limiting, mass of water 22.5. Say if you agree or disagree. Okay. I'll start to work through. I think we've got some contradicting answers, so let's do it together. We've got moles of C3H8 first that we have to find, which is propane, and we're going to take the mass and divide by molar mass. So 20 divided by 3 lots of 12.01 times by 8 lots of 1.008, and just putting in a calculator, getting up Desmos. We're going to 20 divided by exactly that, 01, times by 8 lots of 1.008. And so that gives us about 0.06888359. And keeping numbers exact through your whole working is important. You then need to find the moles of oxygen, which is going to be 50 divided by 2 lots of 16, given that it is diatomic, and 50 on 32 is going to be equal to 1.5625 moles. Okay. Hang on, sorry. I just realized I typoed the first molar mass. It's a plus, not a times. Into my calculator. So this should be 0.453576. Okay. So you're then comparing the molar ratio 1 to 5. You can test it either way. Let's do a multiplication of C3H8. So 0.45 times by 5 is going to be equal to 2.26. And since 2.268 is greater than 1.56, therefore oxygen is limiting, and that's our first part of the question answered. The second part of the question is then going to be with your mass of water produced. So because you know what the mole amount of your limiting reagent is, oxygen, you can then relate that to how much water gets formed. So the moles of oxygen can be related to the moles of water, moles of H2O, in a 5 to 4 ratio. So the moles of H2O is equal to 1.5625 times by 4 on 5 to get the number of H2O moles. Hang on, sorry. Yes, that's correct. which means that you need to do 1.5625 times by 4 and 5, which is 1.25. And the final step to find the mass of water produced is to multiply by molar mass times by 2 lots of 1.008 plus 16, which is equal to 18.016. Putting in the calculator, answer divided by 18.016 gives, sorry, not divided by, times by gives 22.5 grams. And given that the question had 4 sig figs everywhere, 4 sig figs, and all of the periodic table elements are 4 sig figs as well, I would actually leave this to 4 sig figs, 22.52 grams to 4 SF as my final answer. So, it is times by 4 and 5 because you should have less water than you do have oxygen. So if you divide it by 4 and 5, it would imply that you're making more water moles than you are reacting oxygen, and that wouldn't make sense. So that's why it's times 4 and 5. You only have 4/5 the moles of water, in other words. Okay. Well done, everyone. So limiting reagent calculation, hopefully that wasn't too bad. Okay, cool. You can do a practical to talk about the mole ratio of parts in an equation. Won't go through the probably not worth it, but I do want to move on to concentration and molarity. So with concentration and molarity, again, you can do practicals to find concentrations and whatnot. The main thing I'll focus on is just the theory though, because you guys should know what concentration is by now. Concentration talks about the amount of a substance within a given volume, typically. And that would be your molarity, which we talked plenty about in Mod 2. More generally, it can also be a amount of solute present in a specified volume of solvent. You can have dilute or concentrated solutions. You can have saturated and unsaturated solutions as well. Dilute and concentrated meaning either less or more solute per unit volume, respectively, or saturated, unsaturated. Saturated means that you have so much solute in a solvent that you cannot dissolve anymore. Whereas an unsaturated solution would be if you visualize a cup of water, you put a pinch of salt in, you can still put in more salt. But at one point where you dump in so much salt into that cup of water, you wouldn't be able to dissolve anymore. That would be now a saturated solution. Okay, cool. Important formula. It's big for a reason. C equals N on V. It's on your data sheet. You should know what this means. Concentration is moles and volume. And you should be able to calculate a concentration given a mole and a volume, and find moles given a concentration volume, and finally find volume given a concentration and a mole amount. So you can rearrange this equation to several different arrangements where volume is equal to moles on concentration. Moles is equal to concentration times volume. These are also important that arrangements that you will use. Make sure you're comfortable with them. Some simple calculations, but I think what catches more students out at this stage of the year more than anything is the units. Units for concentration come in different flavors. You have molarity, which is moles per volume. You have mass per volume. You have parts per million. And you have these percent concentrations, which are really quite hidden if you haven't seen them before. So we'll talk through those a little bit. We should be comfortable with molarity and mass per volume, but if you get hit by a parts per million or percent concentration, you've never seen it before, you'll get absolutely messed up. So let's talk on those. I imagine by now we have no... Actually, no. This is an important conversion. Converting between molarity and grams per liter, I think a lot of students struggle with this understanding, where you need to go from moles per liter into grams per liter. Students don't know how to do this, but it's really simple. All you're doing is changing the mole unit into grams. So you need to ask yourself, how do you go from moles to grams? And the simple answer is you multiply by molar mass. So if you ever need to change from moles per liter to grams per liter, multiply by molar mass. If you ever need to go from grams per liter to moles per liter, divide by molar mass. It's the same way as changing moles to mass or mass to moles, except you're talking about it in moles per liter and grams per liter. Parts per million is a unit for measuring very low concentrations. You can also have parts per billion. I won't go into that today, but parts per million's units are milligrams per liter, or micrograms per milliliter, or milligrams per kilogram, or micrograms per gram. It can be any of these, and you should be able to convert between parts per million and mass per volume units. So for example, if you had 2 grams per liter, to change it into parts per million, you need to change it into milligrams per liter. This arrangement up here. So 2 grams is 2,000 milligrams. Therefore, if you have 2,000 milligrams per liter, that's the same as saying 2,000 parts per million. At the same time, you should be able to go from you should be able to go from mass per mass concentrations into parts per million, and you should also be able to revert a parts per million. So if you start with, for example, 330 parts per million, you should be able to say that's 330 milligrams per liter. Sorry, milligrams per liter, which then means you would be talking in 0.33 grams per liter if you wanted to convert backwards going that way. Question about flame test colors, I wouldn't say so. That's more Mod 8, Year 12. I wouldn't stress on flame test colors for prelims, no. Unless your teacher tells you, which is always the golden rule of thumb. If your teacher says you need it, because they write your exam. Okay, percentage concentrations rather. These are very commonly misunderstood. And I think for me, it was very confusing until I had someone explain it to me this way. If you get a percent concentration, there's 3 ways it can come. It can come as weight per weight, which is the same as saying mass per mass, weight per volume, or volume per volume. All it means is if you see 3% weight per weight, or 3% mass per mass, it means you have 3 grams for every 100 grams of solvent. 3 grams for every 100 grams of solvent. Or you could say it's 3% weight per volume. 3% weight by volume, which means you have 3 grams for every 100 mils. That's all it means. 3% meaning 3 grams per 100 mils, 3 grams per 100 grams, or 3 mils per 100 mils. So you should be able to convert this then, for each of these, you should be able to convert into a concentration unit that's appropriate. More often you're going to see the top 2 units, where you can change it into grams per kilogram or grams per liter. And that would allow you to get into your concentration units. An important assumption for prelim chem and also HSC chem is if you have a solution that has water in it, water's density is 1 gram per mil, and it is fine to assume that, or 1 kilogram per liter. So if you have a solution that's, say, 20 grams per kilogram, and it's dissolved in water, you can fairly say that this is also 20 grams per liter. That's fair to say. If they specify a different density of the solvent, you have to take that into account, but for the most part, you are okay to assume that water is 1 gram per mil. Okay, cool. Some more questions. Answers at the bottom there. dilutions and standard solutions. So, a dilution is where you take any solution and you add solvent to it. You add more water, for example. The effect of a dilution is when you add more volume, you increase your volume by adding more solvent. Think about how that changes concentration. Type it in chat, and then I'll reveal it. If you increase volume, you will have a decrease in concentration. So dilutions decrease concentration. That is the effect. And for any dilution, you should be able to figure out the concentration after the dilution happens by using the dilution formula. C1V1 equals C2V2. You can also go the long way, just using C equals N on V and solving for moles, and then applying the new volume. But the dilution formula is always faster. The dilution formula has 4 parts. C1V1 equals C2V2. And the importance of each part is that you start with 2 known variables, a known concentration and a known volume. You also will have one of the second variables, either the concentration or the volume that is known. Let's say in this case it's the concentration at the end that you... more typically it's going to be the volume you know, sorry. More typically with the volume you know. You can then rearrange the formula to solve for the unknown variable. So C2 equals then C1V1 on V2. Plug in all your numbers and you find the concentration at the end. Quick example of that here. If you have 100 mils of a 0.25 mole per liter sodium chloride solution, and you dilute it until you make it a volume of 1.5 liters, you can then calculate the new concentration. To do that, you can either do it by the long way, where you solve for moles of sodium chloride, then divide it by the new volume. That gives you the correct answer. Or you can use the dilution formula, where C1 is the initial volume and concentration, and the new volume is 1.5. That will then allow you to find the ending concentration is the same number as that. But it's, in my opinion, quicker. Either's fine, whatever makes more sense for you. Okay. Standard solutions. What a coincidence that you ask. So, standard solutions, how to prepare them. A standard solution, first to define it, is a solution that has a known concentration. A known fixed concentration a known fixed concentration, and you form it through weighing a solute and dissolving it into a volume. So you weigh a solute out, get a known mass, and dissolve it into your solvent. There are steps you follow to make that solution. Mod 6, we talk about it more. There are some conditions that you need to fulfill to have a good primary standard. So the primary standard substance that you choose has to obviously be soluble. You should know its composition. It should be as pure as possible, non-volatile, have high molecular weight for better accuracy, and it should be as cheap and readily obtainable as possible. To prepare the solution, what you would take is you take your primary standard, the substance you're trying to make a known concentration of, weigh it. Say you weigh it and it comes out as 1 gram, or probably be more precise, let's say 1.00 grams. Dissolve it in an initial amount of water. Stir it, mix it, make sure it's all dissolved, and pour that solution into a volumetric flask. So what you've done by this step, because you have a known mass, you can divide by the molar mass if you know its composition, which you should, which gives you a known mole amount. So the moles are known from the moment you get the mass of your solute. Once you place this solution into your volumetric flask and you fill it up to the gradation line, so you would have a gradation line which marks when you've reached the correct volume for this flask. Once you reach that line, with the bottom of your meniscus at the bottom of the line, or bottom of the meniscus in line with the line, that is when you now have a known volume. So this might be a 250 ml volumetric flask, for example. At the point where you reach that line, now you have a known volume. So the two steps combined give you a known mole amount, they give you a known volume amount. And so guess what? Concentration is equal to moles on volume. Plug in your two numbers and now you have a known concentration. That is how standard solution formation works. Find the moles, find the volume, find the concentration. That is it. Okay. C1V1 equals C2V2. Sometimes when they ask you to find the volumes, sometimes you subtract it. Can you explain when that is the case? I'm not entirely sure if I understand what you mean. I'm assuming you're talking about combining of volumes, and in that case you would add volumes, but I'm not entirely sure of the question. Apologies, I haven't answered that really well. You could ask in a different way, I might be able to help better. Okay, cool. And then with any solution you can dilute it. You should be able to calculate the concentration. This is a nice question at the end with serial dilutions. If you do 3 dilutions in a row, what's the concentration of the last solution at the end? Have a go at that in your own time. All right, the final part of this module, module 2, is gas laws. You have a few things to learn. You need to know how gas behaves. You need to know what the gas laws are, what the important equations are that you can use and be asked on in your exams. And that's more or less it. So let's get into it. First of all, with how a gas behaves, we understand that going from solid to liquid to gas, this is the process of applying more energy. The solid just vibrates by itself in place, a fixed structure. When you apply enough energy, the solid starts to move faster, and then it can move freely amongst itself, but it cannot escape the pull of the liquid. And once you have enough energy, at one point gas is able to just leave the solution and it becomes evolved with the gas when you have enough energy. So the whole process and the idea that I want you to have is that gas is the highest energy state that we have. So the way in which it behaves, it is free to move anywhere in space. It is able to diffuse out into an open space and fill the whole volume. Because it's so spread out, you can expand how much volume it takes out, or you can compress down how much volume it takes up depending on the container you put it in. And the volume it takes up will change with temperature, will change with pressure as well. So it all depends on these different variables. And finally, they tend to be lower density because they're so spread out. Flow, I don't really hold any strong opinions on QCE Chem. Obviously, this is HSC focused, but I'm pretty sure the concepts overlap to some extent. It's just taught in a different order and with some other stuff that they teach as well. But I don't know too much about QCE Chem. We just focus on HSC. Kinetic molecular theory. This talks about how when you have gases, which are particles, they move in a particular way and they behave in a particular way when we treat them as ideal gas. So gas moves in straight lines. That's the first thing. When we assume it's an ideal gas, when gas particles collide, the collisions are elastic, which means that they don't lose any energy when they collide together. They don't have any appreciable volume when we assume ideal gas, and this is in our prelim chem, HSC chem thinking for our calculations. We assume our gases are ideal gases. That's the context. We assume that they don't interact with each other, and we assume that the kinetic energy is proportional to absolute temperature. And that is the first thing we need to do. We need to talk about what is temperature, what is volume, and what is pressure. Because without those variables, none of these gas laws actually make sense. Temperature can be thought of as a function of kinetic energy. So the more kinetic energy a particle has, the higher its temperature is. Temperature is a measure of the kinetic energy. We don't need to know this equation. What I want you to understand, though, is that temperature and kinetic energy are related. That is what I want you to understand. And as kinetic energy gets higher, temperature gets higher. Okay. You also have units for Kelvin. Kelvin is an alternate way of measuring temperature, and it starts from 0. 0 Kelvin is the same as negative 273.15 degrees Celsius. And that difference between the two measures stays the same for the whole Kelvin and degree Celsius scale. So once you reach 273.15 Kelvin, you have now reached 0 degrees Celsius. The interval is always the same, and that number's in your data sheet. Okay, the importance of 0 Kelvin and why we don't go any lower. So this is 0 Kelvin is the lowest temperature possible, like full stop. That is it. It's referred to as absolute zero. And it's the temperature where you have zero kinetic energy at all on any of the atoms in the system. Zero kinetic energy. So nothing is vibrating at all. You cannot go colder, you cannot go lower in temperature. You can only go to higher temperatures by adding more kinetic energy, vibrations, and then changing states eventually. Okay, gas volume. Gas volume is how much space the gas takes up, and it will expand to take up the volume of whatever container it's in. So the same amount of gas could take up 1 liter of space if you put it in a 1 liter container. It could take up 5 liters of space if you put it in a 5 liter container. But the variable that changes based on that container changing size is then pressure. As we should know, pressure and volume are related together, where if volume goes up, pressure goes down, and vice versa. So if you have that same amount of gas in a 1 liter container, you take it and you put it into a 5 liter container, volume has gone up, but pressure has gone down. And then the question is, what is pressure? What is pressure? Pressure is a measure of the net force per area from particles colliding with the container's walls. So if you have lots of collisions at high energy against the walls of a container every single second, you're likely to have a higher pressure. There's also partial pressure versus total pressure. Most schools don't even go into this, but partial pressure is the components that make up total pressure. If you add up all the partial pressures, you get total pressure. I won't focus on that too much. You have units of pressure, pascals, atmospheres, bar, torr. You should be able to convert between these using what's in the green there. You can use any of those. And then we arrive at our gas laws. So, gas laws, we should know Gay-Lussac's law is relating temperature and pressure. So pressure is going to be proportional to temperature. Reason being, if you take gas and you heat it up, you will have more collisions against the walls of the container per second, and the collisions are also at higher energy. So the force that you exert against the walls is going to increase. The area is not changed, so that means pressure is going to go up when you increase temperature. A proportional relationship, hence these equations here. We can then use that equation, P1 on T1 equals P2 on T2, to relate starting pressure and temperature with a changed pressure and temperature. For example, if you have 90 degrees Celsius gas being heated to 80 degrees Celsius and the initial pressure was 2,000 pascals, the pressure of the gas after it's been heated can be found by performing these calculations. It's important that whenever you use, and this is a massive, massive, massive flag, do not make this mistake in your exam. If you have degrees Celsius as your temperature and you process it in your formula, you will end up with negative numbers sometimes, and it will always be incorrect. You have to convert temperatures to Kelvin before you process them in any calculation. The only case we can get away with this is change in temperature, because the change in temperature of Kelvin versus degrees Celsius is the same. But if you're using an absolute temperature value, you must use Kelvin. And so once you've changed it, you can basically just process the numbers, insert in your equation, you find 2.4 times 10 to the 3 pascals is the pressure for this system. Okay, so you have Gay-Lussac's questions here, if you want to try any of those. Next relationship, Boyle's law. Boyle's law relates together pressure and volume. So, as we said before, or this is the opposite case. Now, if you start with a volume and you compress down the volume into a smaller space, the same amount of gas into a smaller space, you now have more collisions occurring against the walls because it doesn't take as long for a particle to reach a new wall. And you also have a smaller area over which those collisions are happening. And since pressure is equal to force divided by area, you have more force, you have less area, which leads to an increase of pressure from both of those changes. That is why volume is inversely proportional to pressure, and the equation is instead P1V1 equals P2V2. Boyle's law. You can do the same calculation. Wording of the questions will sound very similar. It's just different variables, and that one's shown there. Practice questions. Charles' law. Charles' law is the relationship between temperature and volume. The idea is that if you heat up gas, it will hit the walls more frequently, and if you're not holding volume constant, you're holding pressure constant instead. Pressure is constant. That will mean you have more collisions against the walls, so a greater force. The only way to keep pressure constant, if you have a greater force, is to also have an increase in area, which is why your balloon will increase its area to disperse this force over a greater area and keep pressure constant, or at least pressure down, not exceedingly high. Balloon is not a perfect example because you would have elastic resistance as well, but there's the idea behind it is that if you push up your force against the walls, the area must increase to keep pressure relatively constant. A bag is probably a better way to think about it because there's not as much resistance. But yes, this is Charles' law. So volume pressure proportional, V1 on T1 equals V2 on T2. And a worked example is shown here as well. Similar, make sure you process temperature in terms of Kelvin. Do not use degrees Celsius. Questions in the chat. For sig figs, do you ignore the sig figs of the temp in degrees? No. So if they give you degrees, the temperature is 20 degrees Celsius, this is still 2 sig figs. You still use it if you use it in your calculation. You still use that as your sig figs too, I would say. Do you have a good way to remember the different gas laws and the respective equations? Unfortunately, no. It's a little bit manual. The only good, I guess, the one to remember that is different to the other two is your Boyle's law, because it's inversely proportional. You sort of just have to do some manual work with attaching the names to each of the laws, but that's the only one I would say that there's a trick, but you do just sort of have to manually remember. And then the combined gas law takes these laws relating pressure, volume, temperature, puts it all together in one. P1V1 on T1 equals P2V2 on T2. There's a very specific use case for this equation where if you have a question that gives you 5 variables of pressure, volume, and temperature and asked for one unknown, you instantly think, okay, combined gas law, 6 variables, I can solve for one of them. And you simply insert into your formula to solve for the answer. Okay. The last law is Avogadro's law, which relates moles and volume if you keep temperature and pressure constant. As you would expect, if you have more of a gas, you should have a larger volume of that gas, and I think this is the easiest one to remember out of the 4. Okay. Once again, flag, big important concept that if you don't get, you lose marks. So you have to get it. So the molar volume is how much volume one mole of gas takes up, how much volume 1 mole of gas takes up, if you're at specific sets of conditions. So you need to know what standard temperature pressure, STP, or standard laboratory conditions are, SLC, because these have specific molar volumes attached, which can shortcut your working. If you ever see that you have 0 degrees Celsius, or 273.15 Kelvin, and 100 kilopascals, you are at STP. So if, for example, you had 1 mole of literally any gas, 1 mole of, let's say, neon gas, you can say that that will take up 22.71 liters of space. Easy. That's it. And then if you have 1 mole of, let's say, another gas, let's say it's helium gas, at 25 degrees Celsius and 100 kilopascals, you can safely say as well, that's going to be 24.79 liters as its volume. So, this makes your working a lot easier, particularly when you have, I guess, less round numbers. They tell you, or you figure out that you have 0.03 moles of neon. You can find the volume that neon would take up by taking the moles, multiplying by the molar volume, which would give you whatever the volume should be, that mole amount of gas takes up. And so this applies for any gas, any at all. It doesn't have to be a specific gas. This rule applies for everything. Okay. And the final thing I'll talk on today is ideal gas. We've already talked about how ideal gas behaves, but the final thing is the ideal gas law. Super, super, super important equations in your data sheet. We should know that the 5 variables are pressure, volume, moles, Avogadro's constant, universal gas constant, and temperature. Universal gas constant is 8.314. This is in your data sheet, and everything else is as we've just discussed before. You can use ideal gas law when you have 3 of the variables, pressure, volume, moles, and temperature, and one of them is unknown. Say you had pressure, volume, and moles, you'll be able to find the temperature. Say that you had pressure, moles, and temperature, you'll be able to find the volume. So ideal gas law allows you to solve for any of these variables if you have 3 of the others. That's when you use it. And these are some examples of when you might do so. So once again, practice questions. And more or less, that is the end of Module 2. The end of the gas laws, end of concentration molarity, end of moles, mole calculations, end of the basic foundations. We've been through it all. So, well done for those of you who made it to this point. We've been here for a long time. Thank you for everyone participating so actively in the chat. As a final thing today, before I get to some of the questions, finally, Catalyst, as I've said before, is an online program. We teach you HSC chemistry 3 to 5 weeks ahead of your class pace. You walk into the classroom knowing exactly what's going on, and it means that you basically are far ahead of your classmates. You know exactly what's going on. You're going to crush your exam with relative ease every term. If you know what you've just learned in the last 4.5 hours, basically you would have learned this about, how many weeks ago? 2 weeks, 3 weeks. You would have learned this 5 weeks ago. All of this already done. And you would have reviewed it with us once before then as well. Plus done a mock exam. Plus you would have done the key concepts question booklets. Plus you would have gotten our question compendium to do questions by syllabus dot point. So the point is we give you everything you need to succeed, and we give it to you well ahead of when you actually sit your exams. Well, from Mod 2 we would have done this obviously during term 2, and you would have learnt it 3 to 5 weeks ahead of your class pace then. So we finished content for Mod 3 and 4 about 5 weeks ago. We finished Mod 4 5 weeks ago. We finished Mod 3 8 weeks ago. But what you get with us, you get outstanding results like our class of 2024. You get the best tutors. So we're all 96 plus HC Chem, we're all 99 plus ATAR tutors. You get our resources, you get our accelerated structure, and you get access to our small online classes, which are all single digit online, so you can get to them from anywhere, and our outside of class support as well, which is around the clock. We push you ahead of your class, you learn faster, you score higher marks. It's really that simple. And if you are keen on enrolling for next term, our Module 5 program, which is the main one for most people, which will be starting in Term 4, or Module 7 program, if you're doing a weird schedule, they start September 22nd. You can have a look for more details on our website and submit an interest/inquiry/enrollment form. That would get us in touch with you. We can give you a call, see if it feels right for you, and see how we can help you out with your journey. But to do that, fill